Hello and welcome. My name is John Horvath. This presentation is another case history about using the cone penetrometer for site characterization, and the particular subject of this case history is the John F. Kennedy International Airport in New York City. I've divided this presentation into segments to facilitate your viewing it. These presentations tend to be rather lengthy, and you may find it helpful to watch it in segments. As you could see, I'm going to start out with some background information. I will talk a little bit about fundamentals about the cone penetrometer and cone penetrometer testing, as well as using the cone penetrometer for site characterization. This is for the benefit of those of you who may not be completely familiar with using the cone penetrometer or using it for site characterization. And then I will get into the case history, talk a bit about site geology and development of the Kennedy Airport site, and then get into the heart of the presentation, talking about the outcomes of the site characterization. I will finish up with some closing comments and observations. Well, starting off with some background material, I created a YouTube channel in 2020 and posted the first in what has become a series of narrated PowerPoint presentations on a variety of topics that relate to my more than 50 years of professional engineering experience, specializing in geotechnical and foundation engineering, both practice and academic research. That first 2020 presentation discussed the geotechnical and foundation engineering history, at least up to that point in time, of the John F. Kennedy International Airport in New York City. And this is a facility with which I have had considerable professional experience, literally going back to day one of my professional engineering career in June of 1972. So I've become intimately familiar with Kennedy Airport and its settings. Construction of Kennedy Airport, and this is how it is referred to both locally and colloquially, and is how I will refer to it throughout this presentation, commenced in 1943 in the middle of World War II, and the airport commenced commercial flight operations in 1948. So it has been in commercial operation for a very long time by this point in time. And over the years, there have been many episodes of expansion of the airport as well as rebuilding of, especially of terminal buildings. And this continues to the present. So Kennedy Airport is not a static facility by any stretch of the imagination. It's undergone many changes, and right now, as you may be aware of, is currently undergoing additional modifications to its terminal facilities. So the point is that geotechnical site characterization is a technical issue of perpetual importance at Kennedy Airport. The 2020 presentation about Kennedy Airport covered a lot of different topics, but one thematic component was about how much site characterization technology had changed over time since the airport was first constructed. And site characterization has changed, especially for coarse-grain soils. And as we'll see, these are the types of soils that dominate the geotechnically and foundation engineering subsurface at Kennedy Airport. This tectonic change in site characterization for coarse-grain soils is really largely the result of the commercial availability and the technological evolution of the cone penetrometer. And the cone penetrometer was first used at Kennedy Airport in the late 1980s. This late 1980s usage is believed to have been one of the earliest large-scale uses of the cone penetrometer and cone penetrometer test in New York City metropolitan area. And this is an area that historically has been resistant to using the cone penetrometer. And I say this as one who has literally lived his entire life either in New York City or the suburbs of New York City. Professionally, I've always been based in New York City or the suburbs of New York City. Although I have worked around the world, I've always been based out of New York City in the New York City area. So I'm very familiar with the state of practice in New York City and the surrounding area. And as I said, the cone penetrometer has been very slow to be adopted here. And from what I see, even though it is used more frequently now, it is not used for the full breadth of its potential, in my opinion. The cone penetration test, however, remains a staple of site characterization at Kennedy Airport to the present and for the foreseeable future. As we'll see, the conditions at Kennedy Airport are really classic conditions where the cone penetrometer works very well. And the cone penetrometer is now in its third stage of evolution at Kennedy Airport. The original late 1980s soundings used an electronic cone that only measured tip resistance and sleeve friction, and I will refer to this as the CPT. By the end of the 20th century, this transitioned to the use of the piezocone, the CPTu, that also measured pore pressures, and more recently in the 21st century to the routine use of the seismic piezocone, the sCPTu, that also measures shear wave velocity. So this steady progression of cone penetrometer technology over time now allows design professionals to overcome the historical laboratory testing disadvantage for performing site characterization of coarse-grain soils. As any geotechnical or foundation engineer knows, obtaining relatively undisturbed samples of coarse-grain soils and bringing them to the laboratory for traditional soils testing is essentially impossible. Yes, this has been done for many years on an experimental research basis, but I'm really focusing on routine practice. Although I have been involved in academia for many decades and done a lot of academic research, my research interests have always been practice-oriented. So I really focus on tools that are of everyday practical value. So this latest presentation revisits Kennedy Airport, but to discuss the cone penetrometer-based site characterization in much greater and much more granular detail than that earlier 2020 presentation. That earlier presentation that launched my YouTube channel was very broad in its content, and I focused primarily on the evolution of deep foundation usage, especially taper-driven piles at the airport. So site characterization was just a secondary part of that original presentation. It's the entire focus of this presentation. Another reason why I wanted to revisit the cone penetrometer site characterization at Kennedy Airport is that in the few years since 2020, there have been some significant technical advances in developing metrics for what we now call screening for flow or static liquefaction. These metrics appear to be applicable to the cyclic or seismic liquefaction that is now an important design consideration at Kennedy Airport. There have also been some new publications involving cone penetrometer site characterization that are potential interest to practitioners and academicians alike. Another goal of this latest presentation, as well as earlier ones that I have posted on my YouTube channel, is to foster greater geotechnical and foundation engineering awareness and use of the cone penetrometer for site characterization, especially for coarse-grain soils, and especially in countries such as the U.S., where, in my professional experience and opinion, there is still a significant over-reliance on the antiquated standard penetration test that, as we all know, is probably the most non-standard in situ testing method that there is in practice. Again, I think we could do a lot more, certainly in the New York City area in particular, and in the U.S. in general, for using the cone penetrometer for site characterization. What motivates me for this presentation and other similar presentations is my firsthand appreciation the wide range of soil properties and parameters that can be inferred from a piezocone or seismic piezocone sounding in soil conditions such as we have at Kennedy Airport that are amenable to using this tool. This is really the direct result of my practice-oriented foundation engineering research that dates back to the late 1980s and continues to the present, as well as my use of the cone penetration test and design practice for many decades. The bottom line is I've seen what can be gotten from using the cone penetrometer nowadays, and I think it's pretty remarkable, and I think we should be using a lot more than we do in practice. Before I proceed further, I believe in professional and ethical transparency. We've seen this very frequently in recent decades. We see articles in the popular press about, it turns out years later that some medical research was sponsored by some business that had an interest, a financial interest in the outcomes of that research. But that wasn't revealed by the researchers at the time. So I think it's important for professionals, for scientists to be transparent about things. So I want to emphasize that I have received no financial compensation from any organization or individual person for any specific purposes of promoting the cone penetrometer, patient testing, preparing this presentation, or any other presentation you see on my YouTube channel. Now, since the 1980s, there have been several organizations and individuals who have provided me raw data, generally in the form of spreadsheet data from cone penetrometer soundings at several locations around the world, including Kennedy Airport. But they have done this on a pro bono basis for my research purposes. My research has been largely interested in tapered piles, taper-driven piles, and coarse-grain soils. But there's been no quid pro quo or expectations from this material being provided to me, other than in several cases there's been a request that the client be kept confidential as to where the data came from or the exact location of these data. And we'll see that in this presentation, that although the data all come from Kennedy Airport, I'm not going to say this specific terminal or this specific terminal owner provided the data, and this is at their request, and I think this is a reasonable request on their behalf. Further, I want to emphasize that my YouTube presentations are not and have never been monetized. I've never received a penny from YouTube for any of my presentations. Now, I am aware that ads appear during viewing of my presentations. I have no control over this. This is something that YouTube started doing a couple years ago. They didn't originally, but they started doing it a couple years ago. It's for their benefit only. I don't get any money for those ads appearing. And the ads are unfortunate, but they're a kind of a necessary evil, I think, to be able to view these presentations at no cost. I may mention the name of an organization or a product or perhaps a person in this presentation. This is for informational purposes only, and I'm not promoting a product or endorsing a product or organization at all. If I name individuals, it's because I want to recognize them professionally for technical information that I've used in this presentation, which I think is certainly an appropriate attribution. So to sum things up, this presentation, as well as all the early ones I have posted on YouTube, I don't have any underlying agenda. All right, this is not a paid promotion of the cone penetrometer or any other technology that I may talk about. I do this on a pro bono basis. I've always enjoyed teaching. It's the reason I went into full-time teaching for almost 30 years. So it's my contribution for advancing the state of knowledge with respect to geotechnical and foundation engineering practice and research. Well, that now brings us to our second segment, and this is a discussion of some fundamentals about the cone penetrometer and cone penetration testing. This presentation talks about what I call the true cone penetrometer, and has certain characteristics. First of all, it has a conical tip with a 60-degree apex angle, as you can see here. The most common cone has a 10 square centimeter projected tip area, although more and more frequently here in the US we're using cones with a 15 square centimeter projected tip area. And the reason we use these larger cones and the results we're going to see at Kennedy Airport will obtain with these larger cones is simply to be able to push the cone to greater depths in fairly hard resistant soils like coarse-grain soils. The true cone penetrometer is pushed into the ground at a constant rate of penetration, and it had its origins in the Netherlands in the 1930s. So for many years in the 20th century it was referred to colloquially, at least here in the US, as the Dutch cone. I entered professional practice in 1972, and for many years after that, whenever I heard someone talk about the cone penetrometer, it was always referred to as the Dutch cone. I suggest you be careful. Nowadays, the term cone penetration test or cone penetrometer is used for a wide variety of other conical penetrometers that have different diameters and installation methodologies. You'll see very slender penetrometers that can be pushed into subgrades by hand to test out subgrades for pavements, for example. You'll see penetrometers that are driven with a drop hammer into the ground, very much like the standard penetration test. So you need to be careful when you hear the terms cone penetrometer, cone penetration test. Clearly understand what exactly the person is talking about. Now, the original cone penetrometers only measured the vertical resistance force to cone penetration. This was done mechanically with a pressure gauge at the surface. And this force was expressed as a stress and given the notation lowercase q sub c. But the miniaturization of electronics in the latter decades in the 20th century and continuing to the present have added additional parameter measurement capabilities. And this started with the measurement of sleeve friction. So friction along the side of the penetrometer just behind the tip. And this is done with what is called a friction sleeve, or in some cases you'll see it called an adhesion jacket. Friction sleeve is the term I see most commonly used here in the US. And you see that there are electronic strain gauges to measure the tip resistance as well as the force in the friction sleeve, preferably independently. Because of ongoing hardware development, the two versions of the cone penetrometer that you see widely available and used at present are the piezocone, again CPTu, measures tip resistance, sleeve friction, as well as pore water pressure. And nowadays this is most commonly done as what we call the U2 location. It's measured on this what is called the shoulder just behind the tip of the cone. You want to be a bit careful. Earlier versions of the cone measured the tip resistance along the face of the cone. This is called the U1 location. Cones typically are either or. Nowadays they're almost always at the U2 location, but you will find some older publications where the measurements were at the U1 location. And there have been experimental cones used in research where pore pressures are measured at both locations, because all other things being equal, the pore pressures can be very different at these two locations, given the complex mechanics of what is going on around the tip. Regardless of whether we talk about the U1 or the U2 location, pore pressures are always referenced to what we call U0, which is the static or overburden water pressure. The seismic piezocone also measures shear wave velocity, capital V sub S. You might see some older publications use lowercase v sub s. And this is done, here's a typical truck from which the cone is pushed from inside the truck. And you see that they have a plate that extends from the truck, and a hammer strikes this plate in a horizontal direction, sends a shear wave through the soil. And this is measured by a geophone that is located within the penetrometer. And if this is done at successive depths, you measure the time difference between the two arrivals, and from that you could calculate from theory the average shear wave velocity. So these are what we call interval shear wave velocity. So when you see a shear wave velocity reported, is basically the average over some interval. And how close this interval is, it could be pretty much anything in principle. However, you have to balance the cost of doing that. As we'll see, for most of the measurements were done at Kennedy Airport that I will discuss, the measurements were made 5 feet or 1.5 meters apart. 1 meter apart, roughly 3 feet apart, is very, very common nowadays. There have been some experimental devices that measure the shear wave velocity of much closer spacings. But it's always an average over some interval between 2 points where readings were taken. I do assume a basic knowledge of the piezocone and seismic piezocone throughout this presentation. If you really know nothing about these devices, you might want to spend some time to come up to speed with things. An excellent English language primer on the piezocone and seismic piezocone is this NCHRP synthesis report that was published in 2007. It was published on the direction of Dr. Paul W. Main, who, as I'm sure you know, is one of the world's leading experts on the cone penetrometer, and I will be referencing his work extensively throughout this presentation. This report was sponsored by the American Association of State Highway and Transportation Officials, as well as the U.S. Department of Transportation, Federal Highway Administration. Now, you will find that since this was published 17 years ago, that some of the material, especially with regard to interpretation of the measured data for soil properties and parameters, is somewhat dated, simply because newer, more accurate correlations and methods have been developed since then. But it is still a very sound document overall, and it's an excellent introduction and primer to the cone penetrometer. So I recommend it highly if you know nothing on the subject and want to come up to speed efficiently. This brings us to the next presentation segment. I want to provide an overview of how we use the cone penetrometer and cone penetration test for site characterization. This will set the stage for understanding the detailed results I will present in a later segment. I've divided this segment into 3 topics. I'll start off with an overview and then summarize the soil properties and parameters we obtain from a cone penetration test, and then finish up with some personal observations of trends I've seen in the states of knowledge and practice of using the cone penetrometer over the last several decades. Okay, starting off with an overview. The arithmetic equations relating data obtained from a cone penetrometer sounding to soil properties and parameters have always been primarily empirical in nature, and these empirical relationships are commonly based on statistical correlation with laboratory testing. Here's a very good example. where we relate relative density of coarse-grain soils to the cone tip resistance. And this is the sort of arithmetic equation you'll typically see in a design manual or a handbook or a technical publication. And as you can see, it's essentially a linear best fit to a set of data. So it's important to keep in mind that these are statistically derived equations. There's, of course, going to be scattering data, as you can see here. And where possible, it's important to see how many pieces of data were used, in this case 456, and also the coefficient of determination, commonly called R squared. As you know, R squared varies from 0 to 1. The closer R squared is to 1, the better the empirical equation fits the set of data. So it's important to keep in mind that, when we see these equations, give us things to a certain number of decimal places, that there was inherently scatter in the original data that went into this equation. Not all of these equations are linear. Here's another example where we relate the peak friction angle measured in a triaxial test to the tip resistance in sand. And again, here's the empirical equation you'll see in a technical publication. Although n and r squared are not given here, you could see that there's a relatively modest amount of data went into this relationship. And of course, there is going to be some scatter in those data. So I'm emphasizing this not to deter you from using these equations, but to appreciate that there is some scatter in the data that went into each of these equations. Also important to realize that these empirical correlations and the resulting arithmetic equations that they produce are constantly in a state of flux. People are doing research around the world all the time on refining these and many other equations for the cone penetrometer. And a lot of cases, even the same researcher will often change an equation over time as new data are obtained. This reality has several aspects that are really mission critical to realize or appreciate to use the cone penetrometer accurately for site characterization. So you always keep these things in mind. First of all, the definition of a best or most accurate empirical correlation between cone penetrometer data and some soil property or parameter is inherently ill-defined. It's a real beauty is in the eyes of the beholder sort of thing. As a minimum, it's going to be time dependent. There's always subjectivity in the form of professional judgment when choosing which empirical correlation, or perhaps an arithmetic mean or average of more than one equation, to use for a given soil property or parameter. I believe that a practitioner or researcher should always state clearly the equation they use for a given soil property or parameter. How do they get this number? They should state this in their published work, so that you, the end user or reader of that publication, can form your own professional opinion about the validity of the calculated outcomes. Nowadays, I think this is especially important when you use commercial computer software for cone penetrometer-based site characterization, as opposed to performing your own site characterization assessments. My observation is that both practitioners and researchers are increasingly using commercial computer software for post-processing cone penetrometer data. For the simple reason it's a lot easier and faster. All right, you pay the money, you get a license to use a piece of software, and you input your data, usually in the form of from a spreadsheet, and you get all these wonderful magical results in 256,000 colors. So it's very tempting. But you, as the end user of that software, should always acquaint yourself with the specific correlation used by that software developer. Every software developer is going to have a bias, and I don't say that in a negative context. They're going to have a professional opinion as to what's the best of these empirical equations to use for a given solved property or parameter. They need to convey that information to you so you know fully how they got all those nice results you see on the screen. This is nothing different than what should always be done when you use commercial software for any other aspect of geotechnical or foundation engineering. All right, you do a slope stability analysis. Well, whose solution do you use? You know, modified Bishop, Jambu, so-and-so, Morgenstern, Price, whatever. If you calculate the axial compressive geotechnical resistance of a deep foundation element, you know, whose method was used to calculate this. So we do this, or certainly should be doing this all the time. All my point is here, this is no different if you use commercial software for site characterization of cone penetrometer data. All the soil properties and parameters I'm going to present subsequently, as well as everything in any of my earlier presentations, are for the most part based on published empirical correlations developed by others. In a few cases, and I try to make this clear, I've used well-established theoretical relationships. In all cases, and this is both this presentation as well as all the earlier presentations you see on my YouTube channel, solution of these equations and the plotting of the calculated results were performed by me personally using an Excel spreadsheet software. Although manual calculation is theoretically possible. As you can see, these are fairly straightforward arithmetic equations. You could theoretically solve them by hand using a personal calculator, although really nowadays it's impractical given the volume of data that is generated by a cone penetrometer sounding. So everything you see in this presentation and elsewhere, I did not use commercial software for any of this. I will note as an aside that, as I indicated earlier in this presentation, I've been using cone penetrometer data since the late 1980s, which is around the same time that Microsoft developed Excel. And I will tell you that the current version of the Excel spreadsheet I use to post-process cone penetrometer data, it's really a much modified version of the spreadsheet I developed decades ago. I've lost track of how many times I have modified this spreadsheet over the years as I see new correlations in the data or whatever, in literature or whatever. Well, there have been countless publications about the cone penetrometer in general and its variants such as the piezocone and seismic piezocone in particular. The most useful practice-oriented published work in recent decades that I found were produced by Dr. Paul Main, who's now retired from Georgia Tech, and Dr. Peter K. Robertson, who's been retired now for some time from the University of Alberta, in conjunction with their graduate students and other collaborators. Drs. Main and Robertson, in my professional opinion, are probably the two biggest experts in the world now and for many years with the cone penetrometer, and pretty much everything in this presentation derives from work that they have published in the open literature. The reason I particularly like the work done by Drs. Main and Robertson is that in addition to their own original research, they have curated and incorporated the published work of many others around the world. So it's not just, you know, Paul Main says this or Peter Robertson says that. They certainly have looked at work of others and incorporated that work into their own thoughts. Now, the bulk of the relationships that I've used for the results I'm going to present subsequently are from the published work of Dr. Main. He's done a lot of work with coarse-grain soils. He's presented his work in many different theme papers. Many of them were keynote lectures at various conferences, as well as PowerPoint presentations at invited lectures. A good way to access these papers and presentations is via Dr. Main's own personal webpage that he still maintains at Georgia Tech, and you can find that via an online search. In addition, more recently, Dr. Main collaborated with this report put out by the State of Minnesota Department of Transportation in 2018, this design manual. Dr. Main was a co-author of this document that you can find online, and many of the empirical relationships for what I used in this presentation can be found in this document. I've also extensively used the published work of Dr. Robertson, especially with respect to soil behavior type and soil structure, sometimes referred to microstructure, that is due to aging, cementation, and other environmental factors. Dr. Robertson is a leading proponent of the concept that the cone penetration test should be used primarily for identifying soil behavior type, not soil particle size and plasticity per se, which was done earlier decades of the cone penetrometer development. And his work nowadays with respect to soil behavior type is recognized globally as the de facto standard. Dr. Robertson has also done a lot of work with soil structure and explaining the difference between the behavioral age of a soil stratum versus its geological age, which are not necessarily the same. Geological age is fixed in time. It's when a soil stratum was deposited. Behavioral age is how a soil stratum behaves, which can vary, as we'll discuss subsequently. Dr. Robertson has also been very generous with making his published work available. He's put many of his publications and narrated PowerPoint presentations on his personal website that you can find online, and he has also co-authored a user's guide that is published by Greg Drilling and Testing, that is a cone penetration test contractor in North America, and Dr. Robertson has been affiliated with them for some years now. This manual is now in its 7th edition, most recently published in 2022, and again, you could find this online. Bottom line is that any geoprofessional can replicate and reproduce the outcomes that I'm going to present subsequently, as well as in earlier presentations that discuss the cone penetration test. It requires a lot of time and effort. I will tell you, as I said, I've been using the cone penetrometer data since the late 1980s, and the current version of Excel spreadsheet is a much modified version of something I've been using now for decades. So this information doesn't come overnight, and this is part of the reason why people like to use commercial software. You know, unless you want to spend a good bit of time and effort to come up to speed on your own, it's very tempting to simply buy or to lease a commercial software package that somebody's already done that work for you. I'm not saying not to do that. It certainly is pragmatic for practitioners, but again, you should at least take the time to acquaint yourself with, you know, if the software says this is the phi angle of the soil, well, you know, which of many empirical correlations did the organization that produced the software use to calculate that phi angle? As I said, these These equations are fairly straightforward arithmetically, but they're simply such a sheer volume of data that you really need to automate it in some way, and a spreadsheet is well positioned for this. Just to give you an idea, when I first started using the cone penetrometer at Kennedy Airport in the late 1980s, you got two pieces of data, tip resistance and friction, every foot, every 300 millimeters. Whereas nowadays, with piezocone and seismic piezocone soundings, you get three pieces of data every inch or two, depending on the cone diameter, every 20 to 50 millimeters. So, a tremendous increase in the volume of data. And as I said, this explains why a lot of people nowadays, including researchers, academic researchers, will use commercial software. Although, as I've said now several times, you need to at least take the time and effort to acquaint yourself with what particular correlations were used in that software. I now want to summarize the soil properties and parameters that you get from a cone penetration test. And this is just a list of things that I'll be going through in detail in a later presentation segment, starting with how you post-process the basic data, soil identification, soil behavior type, and then get into various soil properties and parameters, index properties, fluid flow, liquefaction screening, which is something relatively new but nowadays very important in many cases, the stress state in the soil, the shear strength of the soil, and also how we assess soil stiffness and structure. I want to finish up this presentation segment with some personal observations and professional opinions. As you can see, there are several topics that I want to cover. By way of an introduction, I think it's useful to discuss some of my observations and professional opinions about recent trends and states of knowledge and practice when the cone penetrometer data are used for site characterization. As I've said several times now, I've been an active continuous user of cone penetrometer data for both research and practice since the late 1980s, when all we had were tip and friction data from a CPT. So I've been around and using the cone penetrometer long enough to see the evolution of the piezocone and seismic piezocone. The first topic I want to discuss is net values and normalization. In recent years, there have been movement along two parallel tracks that are in general complementary and synergistic. And the first track has been developing post-process net values of tip resistance and pore pressures that, for example, subtract out the total vertical overburden stress from the net tip resistance to yield a parameter called the net cone resistance, Q net, and subtracting out the static water pressure U0 from the measured water pressure U2 to yield a parameter called the excess pore water pressure delta U. The benefit of doing this is to remove the influence of static earth and water pressures from the raw data in order to better detect trends and changes in earth and water pressures. The other parallel track has been using soil properties and parameters that have been based on data that have been normalized to vertical stress, usually vertical effective overburden stress, and in the process non-dimensionalized. This is an additional effort to level the playing field, if you will, by removing the effects of confining stress and thus allow true trends or changes in soil behavior characteristics to be detected more easily. The use of net normalized parameters is really a logical development. And if you think about it, it follows a now well-established trend in geotechnical and foundation engineering of normalizing parameters to overburden stress. For example, we did this decades ago with standard penetration test N values by calculating what we call N1 values The use of net normalized soil properties and parameters from cone penetrometer data has really impacted every aspect of interpreting cone penetrometer data, and I think is probably the single most significant change in the use of measured outcomes from the cone penetration test in the almost 90 years that this device has been used in practice and research. So that's why I put it at the top of the list of things I want to discuss. The next topic is soil behavior type that I mentioned briefly earlier. There's now an emphasis on interpreting cone penetrometer data for what we call soil behavior type. And more recently, we call this normalized soil behavior type. I'll explain the difference in a bit. That focuses directly on the mechanical performance-based aspects of soil. This bypasses the traditional intermediate step of first defining soil type based on soil particle size, gradation, plasticity of fines that we have used since the beginning of modern soil mechanics in the 1920s. And this was done in the early decades of cone penetrometer usage. As we'll see, people tried to, correlate with plasticity and things like that. As part of this movement to using normalized soil behavior type, we have a dimensionless parameter called the Modified Normalized Soil Behavior Type Index, ICN. Earlier, when we used just soil behavior type, it was called IC, Normalized Soil Behavior Type Index. And this index has emerged as an essential soil parameter in its own right, as we'll see. It's used by itself for various correlations, and it also appears in many, many empirical correlations for other soil properties and parameters. The next topic is critical state soil mechanics. Critical state soil mechanics has been used increasingly in recent years to interpret cone penetrometer data. Coincident with the use of soil behavior type in lieu of soil identification per se has been the increase focused on the concepts of contractive versus dilative volumetric soil behavior. So when you shear a sample of soil, what happens? Does it decrease or contract in volume, or does it increase or dilate in volume? While this is relevant to both the static and dynamic behavior of soil, it has its greatest usage coarse-grain soils and liquefaction potential, as we'll see. As part of this focus on contractive versus dilative behavior is the recognition that this critical state parameter, psi, as opposed to relative density, is really a superior material property for assessing the consistency of coarse-grain soil. Although both academicians and practitioners alike in some places, such as the U.S., tend to be critical state soil mechanics phobic, if you will, and they've been slow to appreciate and make use of this. And I say this in all honesty as one who spent over 30 years full-time and part-time in academic instruction. Here in the U.S., we, for whatever reason, have been very slow to embrace critical state soil mechanics in our education, and as a result, practitioners tend to not be as conversant in critical state soil mechanics as those in other parts of the world. The next topic of note is stress state parameters. Stress state parameters are things such as the yield stress of soils, sigma prime Vm, and the coefficient of lateral earth pressure at rest, Ko. The ability to calculate stress state parameters for all types of soil using cone penetrometer data to complement vertical overburden stress that we've always done manually has been one of the most significant developments. As we know, traditional soil sampling and lab testing historically has only been able to estimate yield stress for fine-grained soils through the very cumbersome process of thin wall tube sampling, followed by odometer testing, a process that is very time consuming, often takes weeks, and consequently is relatively expensive. As I illustrated in an earlier YouTube presentation on site characterization using the cone penetrometer as applied to a case history in New Jersey involving the so-called Hudson Valley Varve clays. Even on a very small project, as I discussed in this case history a few years ago, where there were only 2 odometer tests, and as we'll see, there was only 2 cone penetrometer soundings done, one piezocone, one seismic piezocone. The cone penetrometer really provided a tremendous amount of data for this very complex site that had a very complex stress history. The bottom line is that stress state estimates based on a combination of cone penetrometer data and, where appropriate, and fine-grained soil odometer data are very cost-effective and provide much greater insight and therefore reliability in the interpreted outcomes. And just for those who have not seen that earlier YouTube presentation, I just want to summarize some of the key results that were relevant to stress state. Here I'm showing you the plotted results of yield stress from the one piezocone and one seismic piezocone sounding that were done for this very small project in New Jersey, a site that was underlain by an extensive deposit of glacial-lacustrine soils. So what we're looking at here, and these are all Excel plots, we're looking at vertical effective stresses. Stresses averaged over plus or minus 150 millimeters, 6 inches, as well as median values over plus or minus 150 millimeters, 6 inches. This idea of taking arithmetic means or averages or median values is a technique that has been suggested and I have found very useful, especially for sites where we have a lot of scatter in the data. And then this very complex site in New Jersey, we see quite a bit of scatter in what we're looking at here is the interpreted yield stresses from the 2 cone penetrometer soundings. By either taking averages or median values, we try to reduce some of the noise, if you will, in the data to better observe trends. So we see in each of these plots, I have the overburden stresses in brown, solid, and dashed lines, and then the yield stresses as interpreted from the cone penetrometer data. Each of these data points is at every 50 millimeters or 2 inches. These soundings were done with cones that had a 15 square centimeter tip area, projected area. And in summary, this site, we had a Holocene superficial deposit of miscellaneous, mostly sand fill over a very thin layer of organic clay. This site had originally been the floodplain of a freshwater river. Then we had a fairly substantial stratum of Pleistocene glacial outwash sands and a rather substantial deposit of glacial-lacustrine Varve clays. Had 2 distinct facies. We had an upper zone that was on the coarser side, a lot of silt and fine sand, and a lower zone that was more silt and clay varves. And this extended down to glacial till and ultimately sedimentary bedrock. So a very complex glacial site in terms of depositional history and concomitant stress history. And there were 2 odometer tests performed on thin wall tube samples. There were a number of conventional borings done for this project as well. And here you see the yield stresses interpreted from the odometer tests. I did these interpretations personally. This was a project that I had a small consulting role in. So I did these interpretations. I used the Burmester method. I know virtually everybody in the world uses Casagrandi's method, and yes, I will use that too, but I find Burmester's method, which is not widely known, provides much more reliable interpretation of yield stress. But in any event, the interpretation of yield stress was something I did independently. And I will point out before I looked at the cone penetrometer data. So this is one test result, and here was the other test result. And if you just looked at the two interpreted yield stresses from just the odometer data, you know, it was hard to make of what was going on here. But when you look at these data in the context of estimates of yield stress from the cone penetrometer soundings, I think things make a lot more sense. We see that there's very clearly a trend in yield stress, and this lower odometer test actually picks up that trend very nicely. The upper odometer test is not wrong. You see it matches a number of pieces of data from the cone penetrometer soundings, but these outlier higher values of yield stress, these are probably perhaps intermediate desiccation layers, things like that, during the glacial clustering deposition, possibly some re-advance of the glacier, ice loading, whatever. So my point is, if we look at things together, we see that the odometer data and the cone data really are in consonance, but the cone data give us a much better picture of the overall trend in yield stress, and appreciating that there are some localized zones where we have some higher yield stress, perhaps due to desiccation or other natural factors. So again, what I'm trying to show you here is that you can get a lot of information from cone penetrometer soundings, and they certainly fill in the gaps in information from traditional odometer testing of fine-grained soils. Moving on, next discussing soil stiffness. The evolution of the seismic piezocone into a tool for routine practice, and on both large and small projects. Again, that small project in New Jersey I just referenced, there was only one piezocone out of the two cone soundings that was done. It's really been game-changing development. This is because when we measure shear wave velocity in a seismic piezocone, this allows for significant advancement in the form of quantifying small strain soil behavior to complement the traditional cone penetrometer measurements of tip resistance, friction, pore pressure that really reflect large strain soil behavior. Specifically, the shear wave measurements allow a theory-based calculation of the site-specific soil stiffness as defined by the small strain shear modulus Gmax. And I should note that Gmax seems to be the preferred notation in the US. Most of the rest of the world seems to use the notation G sub G0 or G0. These are the same parameter, just a notational difference. And we're going to be discussing this issue of the shear wave measurements quite extensively in later segments. The next topic is soil structure. And again, this relates to things we get only from the seismic piezocone. It gives us an understanding that soil stiffness is defined by soil rigidity, which is the ratio of stiffness to strength, is not due solely to confining stress, but also influenced by what we nowadays call soil structure, sometimes microstructure, that is due to aging, interparticle natural cementation, and other factors related to the natural environment in which the soil exists. Where the cementation can come from, for example, has been found with the Connecticut Valley Varve clays, is, for example, due to carbonates in the groundwater from the natural limestone deposits in that region. Of relevance, the Kennedy Airport is more than 20 years ago. Fellinius and his co-authors noted in a technical paper that the setup, or freeze as is sometimes called, which was the temporal increase in axial compressive geotechnical resistance of driven tapered piles in coarse-grain soils at Kennedy Airport, were clearly related to an increase in soil stiffness around the pile, not strength. So collectively, these things related to soil structure again give us an understanding that the behavioral age of a soil, as I mentioned previously, is not necessarily the same as the geological age. There's only ever one geological age. It's when nature placed a soil stratum. However, the way a soil behaves, does it behave like a young soil? Does it behave like an old soil with some aging effects? That can be reset, all right? The behavioral age of a soil can be reset as many times as you want by any number of natural or human mechanisms. Earthquakes especially can reset the behavioral age of a soil. Another soil structure behavioral issue we've seen a lot of attention of in recent years is the behavior of fine-grained soils in particular, and Dr. Main has done a lot of work in this area. So we put this all together, and we now realize that most of these empirical correlations I alluded to earlier for cone penetrometer data are based largely on what we might call mainstream soils. And you see in the literature, these are variously referred to as young soils, well-behaved, unstructured, insensitive. Colloquial terms such as hourglass sands and vanilla clays are used. But all of these terms mean soils that are basically in the mainstream. There are also soils, both coarse and fine grain, that are not in the mainstream. And these require some special assessment. And you need to, the point I want to make here is you've got to be very careful because a lot of these empirical correlations do not work with these non-mainstream soils. Fortunately, the shear wave data from cone penetrometer, seismic cone penetrometer, piezocone soundings, as well as the usual QCFS and U2 data from a piezocone and seismic piezocone, in the case of fine-grained soils, provide metrics for evaluating whether or not a soil is mainstream or not. So the point is that we have ways of detecting whether a coarse or fine-grained soil is mainstream or not, but it does require the use of a seismic piezocone and shear wave measurements. The next topic is liquefaction. Cone penetrometer, as you probably know, has been used for many decades now as an alternative for soil profiling as opposed to the standard penetration test for assessments of cyclic, also known as seismic or dynamic liquefaction of a coarse-grained soil. This is when we have a short-term increase in pore pressures as a result of multiple rapid cycles of shear stress with a concomitant reduction in effective stress and shear strength of the soil as the pore pressures increase. And under such conditions, it can be analytically useful to envisage a coarse-grained soil as exhibiting an undrained strength, something we normally just apply to fine-grained soil. I'm not going to get into this Application of the cone penetrometer. This has been covered for many decades in countless publications. What I do want to focus on is more recent research by both Drs. Robertson and Main that are focused on what we call flow or static liquefaction. And this is something that can occur with loose, granular, usually human-placed deposits such as mine tailings and hydraulic fills. And it can occur with naturally deposited soils that have a similar consistency and particle gradation. But really, things such as mine tailings and hydraulic fills have been the focus of this research for explaining failures of impoundments, for example, of mine tailings. In the case of flow or static liquefaction, there's some trigger event that causes a sudden brittle failure that is a result of rapid volumetric contraction of the soil skeleton. So we have very, very loose granular materials that we have some sort of trigger causes the particles to collapse into a denser arrangement. And this results in a short-term increase in pore pressures. And again, this produces a reduction in shear strength to a residual undrained value. So we kind of broadly get the same result of cyclic liquefaction without the back and forth shaking as cyclic liquefaction. There just has to be a single shock to the system, if you will, to trigger a flow or static liquefaction. And very often it's not clear exactly what this trigger is. It's just because there's any number of triggers that can develop. Note that soils susceptible to flow liquefaction extend beyond coarse-grained soils into so-called transitional soils that may have a significant fine content, such as a sandy silt. The point being, there's a broader category of soils that are susceptible to flow liquefaction as opposed to cyclic or seismic liquefaction, which is usually restricted to coarse-grained soils. And as I noted, there's a much wider range of trigger events, both static and dynamic, that can cause flow liquefaction, whereas cyclic liquefaction is simply a result of a dynamic event, such as an earthquake. There have been two separate but complementary efforts with respect to the cone penetrometer and flow liquefaction, and they all rely heavily on critical state soil mechanics and the concepts of contraction and dilation I mentioned earlier. And this has resulted in a number of properties and parameters that are used for what we call liquefaction screening to identify soil strata and layers within a stratum that are potentially liquefiable or susceptible to flow liquefaction. Such soil properties and parameters, in my mind, are an extension of index properties, and I'll address them in a later presentation segment in that context. Separately but parallel has been development of relationships for estimating the residual undrained shear strength of flow liquefied soils based on pre-liquefaction cone penetrometer soundings. And I'll discuss these later in the context of shear strength. I'd like to close out this segment with a few comments. There have been remarkable advances, I think, in recent decades in terms of the amount of information that we can extract post-process from seismic piezocone data in particular. However, I've also come to appreciate we have to be careful and how these data are interpreted and to use those data intelligently. As I said, there's been a tremendous increase in commercial software that is available to do this data interpretation. But it's really important that the end users of those data understand what is going on. You can't use them blindly. And if you think about it, that's true of any computer software that we use in geotechnical or foundation engineering. I mean, you can't use software to calculate the axial compressive geotechnical resistance of a deep foundation element without understanding the nuances of the different solutions that are available to do this. Settlement of a shallow foundation, slope stability. All right? Think of any topic in geotechnical or foundation engineering where we have used computer software for many decades now. We understand that you need to appreciate and understand the differences between the different theories or solutions that are solved by that software. And the same thing goes for site characterization using the cone penetrometer. The end user has to be very aware of what was done. Well, this brings us to the next presentation segment, where we're going to start discussing the case history specifics of Kennedy Airport. And in this segment, I'm going to discuss the site geology and development history so that you can understand the subsurface conditions in which the cone penetrometer soundings were made. So here's a list of the topics I'm going to cover. After some introductory comments, I'm going to talk about the overall geological setting, discuss seismicity, which has become very important in recent years, and then summarize the site development history to bring us up to the present day. The geology and site development history of Kennedy Airport were really discussed in quite a bit of detail. First of all, in a 2014 white paper that I wrote, and this paper is available on the website ResearchGate. Also discussed the site history in detail in my 2020 YouTube presentation dealing with the geotechnical and foundation engineering history of the airport. So here is the white paper that I wrote. This has the most detailed information about the development of the airport, and this earlier presentation on my YouTube channel contains a summary of what is in the white paper. I'm only going to provide a summary of the summary here because I've covered a lot of this information already in these documents. So as I said, I'm only going to summarize really the key features, major milestones, so that we can see the setting and context for the site characterization that we're going to talk about in the following segment. Well, in terms of the overall geological setting, let's start off with an overview of things. What is shown here is highlighted in green is what is known as the Atlantic Coastal Plain Physiographic Province. Covers much of the east coast of the continental United States. And there are really several key aspects of this physiographic province for our discussion. First of all, here is Kennedy Airport, which is at the very, very northern tip of the physiographic province, literally where this physiographic province begins on the edge of New York City. This province is characterized by, first of all, as a former tectonic plate boundary. All right, this was a former collision zone when North America, South America, and Africa all collided to form Pangea, and then subsequently separated to form the Atlantic Ocean. So we have a lot of relict faults, both ductile faults as well as brittle faults, that remain. So even though this is an intraplate area at the present, there's quite a bit of faulting here, and as we'll see, a modest seismic potential as well. Now, not only the northern end of this physiographic province was subjected to Pleistocene glaciation, and as we'll see, that included Kennedy Airport. And the entire coast of the east coast of the United States has been subjected to post-Pleistocene sea level rise, which in this area has been about 120 meters or about 400 feet. Moving on now to crystalline bedrock. If we take a geologic profile from northwest to southeast through an area of interest, and here's the approximate location of Kennedy Airport. Here's the crystalline bedrock, and as this geologic profile indicates, there is a regional slope of the crystalline bedrock towards the southeast out into the Atlantic Ocean. Here we see the edge of the Atlantic Ocean here, Jamaica Bay. These are features that I'll point out subsequently, and certainly Jamaica Bay figures prominently in things. The depths of bedrock within the limits of Kennedy Airport are typically of the order of about 700 to 1,000 feet, so about 200 to 300 meters below the present ground surface. So bedrock per se is not a factor, other than certainly it is the source of any seismic waves that propagate up through the soil column. We talk about the pre-Pleistocene soil strata. As I said, Kennedy Airport is at the extreme northern edge of the Atlantic physiographic province. Much of this physiographic province is underlain by older layers of coarse and fine-grained sediments that geologists will often map as poorly consolidated sedimentary rock. Underneath Kennedy Airport in general, and Long Island in particular, where Kennedy Airport is located, we have a sequence of Cretaceous soils. These soils are not important for the geotechnical and foundation engineering aspects at Kennedy Airport, but certainly they are regionally very important because they are sources of groundwater for human consumption and other potable water supplies. So these Cretaceous sediments tend to be very important underneath Long Island in general, and for many other areas along the east coast of the United States, as they provide groundwater to a lot of communities. And there are the usual issues with saltwater intrusion coming in from the Atlantic Ocean that are our concern as well. I discussed these things in my white paper that I mentioned previously. I'm not going to get into that in this presentation. We do need to discuss in some detail the Pleistocene geology, because this is really what affects Kennedy Airport geotechnically and foundation-wise. The Pleistocene epoch is really the most significant geologic event that impacts the geotechnical and foundation engineering design at Kennedy Airport. Because of the significance of the Pleistocene throughout the New York metropolitan area, it has always been a subject of a lot of geological research, and this research continues to the present. This is important to appreciate because geologists are constantly revisiting and reinterpreting our understanding of the Pleistocene epoch, and there has been some really significant reinterpretations over the last several decades. I'll touch on some of them in this presentation. Others I talk about in the earlier documents that I mentioned. There are a number of aspects of this both direct and indirect of this ongoing research. First of all, the types of soil are predominantly granular in texture that were deposited during the Pleistocene really impact the foundation selection at Kennedy Airport and have since day one, going back to the 1940s and continue to the present. The consistency, the density, if you will, of these granular deposits has further impacted foundation selection with respect to the seismic history of the New York City region, which certainly has undergone tremendous amount of change in the last few decades in terms of our understanding. Because of the coastal location at Kennedy Airport, the post-Pleistocene sea level rise has certainly impacted the Holocene soil deposits as well as groundwater conditions, and as we now know, will continue to do so even more in the future. Now, in terms of the glaciers that impacted Kennedy Airport, this graphic shows the limits of the Pleistocene glaciation in North America. And what's relevant here's Kennedy Airport down here. Kind of an interesting location. As I said, it's the extreme northern edge of the Atlantic coastal plain province, but it's also the extreme southern edge of the Laurentide ice sheet that came down out of Canada and impacted the New York City area. This is an older geologic map of Long Island, but it suits our purpose as well because it shows what Long Island looked like over a century ago before there were a lot of human changes in some of the coastal regions. Here's the New York City area in general, and here's Kennedy Airport in particular. And as you can see, here's the Atlantic Ocean, and here is Jamaica Bay, which is connected to the Atlantic Ocean. And here comes down the Laurentide ice sheet. Now, when I first was taking geology in the 1960s, an undergraduate student at Columbia University, and for some years thereafter, the prevailing thought was that one Pleistocene glacier did it all in terms of creating Long Island to begin with on top of the Cretaceous sediments, in terms of shaping geomorphologically Long Island and the surrounding area. So for a long time, there was this one glacier did it all view of life. Well, beginning in the later decades of the 20th century and continuing to the 21st century, that changed. It's now understood that the Laurentide ice sheet consisted of numerous separate advances and retreats over a period of time. And in particular, there were two components of this ice sheet referred to as the Hudson lobe that came down the Hudson River Valley and the Connecticut lobe that came down the Connecticut River Valley. And it appears that these two lobes kind of met, not quite head on, but kind of at an angle. They ran into each other in this general area here. And this created a feature that I refer to as the Jamaica Bay salient. Right? If we look at the south shore of Long Island, we see these are all barrier beaches that were deposited during post-Pleistocene sea level rise. But Jamaica Bay is kind of interesting because we have this kind of inverted U-shaped, horseshoe-shaped indentation. And I think one interpretation is that the reason we have this rather interesting feature here, that is Jamaica Bay, can be interpreted as the end result of the Connecticut lobe and the Hudson lobe of the Laurentide Glacier kind of meeting head on, and neither one of them could advance. And these create a feature that we can call the last glacial maximum LGM reentrant. So it appears it's possible that this area was really not affected by these glaciers. And regardless, we see that Kennedy Airport is kind of really in the mix of all this. So we have a potentially very complex geologic setting here in terms of Pleistocene geology at Kennedy Airport. And I'm emphasizing this because this will tie into some things that I'll bring up towards the end of my presentation here. So if we go back to our geologic profile and now look at the Pleistocene geology, we have a number of strata that occupy about the first 200 feet or 60 meters under Kennedy Airport. And of these strata, the most important is the upper Pleistocene deposits that are technically known as the Upper Glacial Aquifer, UGA. This was originally a groundwater table aquifer, as we could see in the upland areas beyond Jamaica Bay, but is now a confined aquifer, as we'll see, within the limits of Kennedy Airport. And this UGA totals in places about 125 feet or 40 meters under Kennedy Airport. There is some variation in this thickness, but this is a good average to bring up in this discussion. Now, the bottom line is this upper glacial aquifer has always been the foundation-bearing stratum for all structures at Kennedy Airport. So whether it's a building or an elevated roadway or an elevated railway, even the large light towers in the parking lots, these are all supported on deep foundations that extend into the upper glacial aquifer. Well, as I said, geologists reinterpreting the upper glacial aquifer, or the Pleistocene geology in general of this area, has been a very active area of research in recent decades. This is from a paper by Cheryl Moss. Cheryl Moss is a professional geologist in consulting practice in the New York City area. Has authored a number of very, very nice papers, either individually or in conjunction with other geologists. You can find a lot of her work online. Very, very nice work. Geared towards geotechnical engineering. She worked for a geotechnical consulting firm. But relevant to our current discussion is the fact that the upper glacial aquifer is now reinterpreted as consisting of three formations, known as the Belmore, the Wantagh, which in older literature is referred to as the 20-foot clay, and the Merrick. So Belmore, Wantagh, Merrick, we'll be seeing these names, especially Belmore and Merrick, as we'll see. We'll be seeing these names quite a lot in the remainder of this presentation. But this relatively recent paper by Ms. Moss is very, very characteristic of this, as I said, recent geological reinterpretation that has been going on in recent decades. Well, moving on to the Holocene, what we're looking at here is a plot of sea level going back about 1 million years. And we want to, again, this is from a paper by Cheryl Moss. We want to focus on the late Quaternary, about the last 140,000 years. This is of greatest interest to us. Here's sea level in terms of meters below the present. And of greatest interest is what we call MIS1. MIS stands for Marine Oxygen Isotope Stage. And this is a metric that is now used for judging climate temperatures. And you see that the Pleistocene has been broken up into several MIS episodes. We're most interested in the last 14,000 Ka is kilo years or thousands of years, so the last 14,000 years, where we've seen sea level go from the last glacial maximum, which was the Wisconsin here in the New York City area, has gone up about 120 meters or 400 feet, as I said, to the present. And in the process of doing so, has created a stratum that I will be referring to as the Holocene organics. And these are a combination of organic clay and in some places organic clay with a topping of peat that cover the area of interest to the present discussion. And we can see that by looking at this U.S. Geological Survey topographic map from 1891. And here is the future site of Kennedy Airport. And as you see, this straddles the open water of Jamaica Bay, which the bottom soils are organic clays, as well as some marine tidal marsh areas that consist of peat on top of organic clay with some tidal creeks going to upland areas. So this is the general conditions on which the site of Kennedy Airport was created. Before moving on, I want to point out two things. One is this rail line, which is originally a branch line of the Long Island Railroad, is now part of the New York City Transit Authority subway system. This has been around a long time, so it can and exists in the present. So this serves as a convenient reference point when we switch between various maps and aerial photos, things like that. And another feature that is important is this kind of boot-shaped deposit we see here of land. This is Idlewild or Long Neck Point. There are a variety of names used for this feature in the published literature and maps that you can find. And you'll see why I highlight this particular location subsequently. This is the oldest aerial photo I can find from the 1920s of this particular area, kind of taken from the same vantage point as the topo, looking towards the north. We see this rail line that I noted over here. Here's Jamaica Bay, of course. And the future site of Kennedy Airport is here and kind of off the photo to the east or right. In case you're curious, this photo shows the construction of Cross Bay Boulevard. This is a local road that exists in the present. And this is of interest because the boulevard was created mostly by hydraulic filling on top of the marine tidal marsh. All these light-colored areas, this is sand that was dredged up from Jamaica Bay, Pleistocene sand dredged up from the bay and pumped hydraulically to create landfill. Relevant because this is how Kennedy Airport was created, by hydraulic filling. So the same process we see here in the 1920s was used in the 1940s to create the airport. Well, we now want to move on and talk about seismicity a bit. One of the most significant outcomes, or arguably the most significant outcome of recent geologic research that has impacted geotechnical and foundation engineering practice at Kennedy Airport, has been the recognition that there is a sufficient seismic potential in terms of magnitude and frequency of occurrence of earthquakes in the New York City metropolitan area to warrant consideration of the effects of direct shaking from an earthquake, as well as the potential for seismic liquefaction, where relevant, and some would argue tsunamis in coastal areas as well, in routine practice. as we'll see, earthquakes have always been there. It's not like, gee, earthquakes only started happening now. They've always been here in the New York City metropolitan area. It just is, it was not until the later decades of the 20th century we began to appreciate that, hey, we ought to start noticing these things in routine civil engineering design practice. So as I said, this seismic appreciation only evolved toward the end of the 20th century. I can remember, again, as an undergraduate in the 1960s taking geology. Geologists would say, well, yeah, we have these things called earthquakes, but, you know, they never happen here in New York, so we don't have to worry about them. That was it. That was all I learned about seismicity as an undergraduate. Well, we now know it's quite a bit different. And it's found its way into codes, and as we'll see, has had a profound impact on foundations at Kennedy Airport. In particular, the potential for seismic liquefaction within the upper glacial aquifer, which again is the bearing stratum for all foundations at Kennedy Airport, has led to the need to install much deeper deep foundation elements than had been done for the first several decades of construction. And later in this presentation, I'll put some specifics on this, and you'll see quite a bit of difference in the way foundation engineering was done in the first several decades at Kennedy Airport, the way it is done now. So this potential for seismic liquefaction has also led to the need to improve site characterization at the airport. We need to evaluate liquefaction potential better. And cone penetrometer soundings are really a superior site investigation tool for both seismic liquefaction screening as well as deep foundation design. So the cone penetrometer, if you will, is really made for the type of conditions we have and needs we have at Kennedy Airport. Well, this map comes from a geology publication, again, part of the reinterpretation of geology, seismic geology in this case, and it shows the epicenters of all known seismic events from the colonial era up to 2004, and you see the symbols in terms of size and color reflect the magnitude of these events. I want to call attention to two events. First of all, here's Kennedy Airport here on the shore of Jamaica Bay, and the most significant event is one of 1884, believed to have been epicentered in the Atlantic Ocean just south of Jamaica Bay, had an estimated magnitude of about 5.2. More recently, on the south shore of Long Island in 1937, had an event of estimated magnitude of 3.5. This is another geologic assessment from a different research group at Lamont Doherty Earth Observatory of Columbia University. Again, discussing known earthquakes from the colonial era, this case up to 2001. And here's Kennedy Airport. And this is a tabulation, at least as of 2001, of the largest earthquakes near New York City. And here we have the 1884 event we talked about, or noted previously. And lo and behold, it's really at the top of the list. Largest known event during this time frame, and I can tell you it has not been exceeded since. What's interesting is that it was felt from Virginia all the way up to Maine, and this is very characteristic, as you probably know, of East Coast earthquakes in the United States. Even fairly modest earthquakes have a rather significant felt distance. More recently, there was an earthquake of similar magnitude in Virginia, and this, for example, caused damage to the Washington Monument in Washington, D.C., and certainly was felt up and down the East Coast. The later 1937 event still makes this list down here. its claim to fame as one of the few earthquakes that was epicentered beneath Long Island proper. And by the way, you can see from this list there have been earthquakes felt within Manhattan Island. Here's Manhattan Island here. There have been several earthquakes epicentered in Manhattan Island. We just had one a few weeks ago. It was epicentered here in Astoria, Queens. Down in the 2-something range, large enough to be felt. And these seem all to be associated with the so-called 125th Street or Manhattanville Fault. The brittle faults through the New York City and southern Westchester area up here that are the result of being plate boundary, they all tend to trend from northwest to southeast. They all tend to go in this direction here. So the 125th Street or Manhattanville Fault, this is the largest known brittle fault on Manhattan Island. In fact, if you look at old topographic maps, it almost cut the island in half. Anyway, this brings us to the last topic of this presentation segment, and that is the site development history, or at least an overview of site development history at Kennedy Airport. So let's begin the discussion by going back to our 1891 topo map and the features we identified previously, the rail line and Idlewild Point down here. In the early 1940s, there was hydraulic dredging of the Pleistocene sand from within Jamaica Bay, deposited on the wetland here to create an area that eventually covers about 5,000 acres or about 2,000 hectares. And this is the result we see more or less in the present time. And this is the central terminal area for the passenger terminal areas at Kennedy Airport that I will be referring to throughout the remainder of the presentation. And this has been the area where there has been a lot of activity over the last decade or so that continues to the present. These terminals have been appearing, disappearing, changing sizes, things like that. But the basic airport has remained fairly static for some period of time. So this transition from marine tidal wetlands to airport, what I called from wetlands to wings in my 2020 presentation, did not occur in one step. There were some important changes that occurred along the way. Here's a 1924 composite aerial photo of the area that eventually became Kennedy Airport. Here we see Jamaica Bay. This was clearly taken at low tide. There's a tidal range of, maybe about 2 meters, 5 or 6 feet roughly within Jamaica Bay. And we could see from the darker areas where there's channel, these are probably mud flats at low tide, that this aerial photo was likely, or the sequence of aerial photos was taken at more or less low tide. Any event, here's the central terminal area, again to give us a point of reference. The rail line I have been referring to is off to the side here, so it does not show up on this sequence of photos. And these numbers 1 through 8 are the designations that have been used in recent years to indicate passenger terminal areas. And I highlight 5, 6, and 7 in red because this was the area where the original passenger terminal as well as the original control tower for the original 1948 version of the airport when it opened was located up in here. So when I first started working at Kennedy Airport in 1972, the terminals were referred to generally by who the primary airline occupant was of the terminal, or if it was used by a variety of airlines. For example, there used to be a building called here where's now Terminal 4, used to be called the International Arrivals and Departures. This was the home to dozens of small national airlines of countries from around the world that maybe only had a couple of flights a day in and out of Kennedy. But in later decades, they've been given to using terms like Terminal 1 and Terminal 4, things like that. So that's why I use these number designations. In any event, to tie things into things we've talked about previously, here's Idlewild or Long Neck Point, and my research showed that this was a very active area of development from sometime in the late 1800s to the 1920s. Hard to believe now, but this area in the 19th century was pretty undeveloped, and Jamaica Bay was viewed as a recreational area, and there was actually quite a bit of development here, including construction of this combination lighthouse, water tower, observation tower. And from things that I found online, there were literally thousands of timber piles driven to support buildings, to support piers, bulkheads, a lot of riprap and material dumped in to create breakwaters, things like that. So this was actively developed as a recreational area, not only in and of itself, but as you could see, there were roadways leading out to the upland areas. What happened in the 1920s? Well, there was a lot of contamination of Jamaica Bay by untreated sewage, simply dumped in from all the surrounding Brooklyn, Queens, and ceased to be desired. Let's just say it ceased to be desirable as a recreational area. So there was kind of a sudden collapse and abandonment of this development here. However, about 1930, they built a golf course called the Idlewild Beach Golf Club. And as best as I could determine, although it was a little bit difficult, this was the area that was occupied by the golf club. There was some placement of soil here to create the golf club. Golf course, there were some buildings, clubhouse and usual buildings such as that. So the point I'm getting at is we didn't go from nothing to an airport with nothing in between. There were some areas which had substantial development that has now been buried under the airport property. And if we now superimpose our 2012 aerial photo of the airport, this area here is the former Idlewild Point development. This area here is the former golf club. And again, there were roadways and things like that going out. What's the point of this? The fact is that we find obstructions. Fortunately, I would think, there has been virtually no building or nothing requiring deep foundations in this area formerly occupied by Idlewild Point. I think one would find thousands of old timber piles, riprap, building foundations. I think there's an enormous amount of old foundations under this area. I have seen borings. I have seen cases, for example, where people try to drive test piles within the central terminal area and ran into old concrete several feet below the surface. So there are remnants of buildings and roadways that do impede construction in the present day. And that's the main reason I'm talking about some of these things. Well, if we complete our geologic profile of Kennedy Airport in the Holocene, going back to profile and all I've shown you previously, on top of the upper glacial aquifer and Holocene organics, we have a stratum I refer to as the Holocene fill. And this is basically the Pleistocene sand that was dredged up from Jamaica Bay and deposited hydraulically to create the airport. So in the subsequent, the next presentation segment, where I get into site characterization in detail, I will be repeatedly referring to the Holocene fill, the Holocene organics, and the upper glacial aquifer in my presentation. So that now brings us to the heart of this presentation, which is discussing the site characterization outcomes from the cone penetrometer data. Here's a list of topics I'm going to cover in this presentation segment. As you can see, it's quite extensive. I will have some introductory comments and then cover the various technical subjects that I had enumerated earlier in this presentation and finish up with some personal observations. Well, let me start off with a prologue to give some background and context to the things I'm going to discuss. The current possibilities for site characterization based on the piezocone, the seismic piezocone soundings for geotechnical and foundation engineering applications, and with a focus on coarse-grain soils, are explored in this presentation segment. The data I'm going to use were obtained from two sources at Kennedy Airport. There were 12 CPT, and that's just the original basic cone with tip and friction measurements only, soundings that were performed within the central terminal area in the late 1980s under the direction of the Port Authority of New York and New Jersey Engineering Department for multiple components, structures, and roadways that were associated with the JFK 2000 redevelopment project. The Port Authority, as it is referred to here locally in the New York City area, has been the operator of Kennedy Airport since the 1940s. The airport property is technically owned by the City of New York, but they have leased it to the Port Authority for operation from the beginning. Also, as I discuss in the white paper I referred to earlier, as well as my 2020 YouTube presentation, most of the construction at Kennedy Airport has occurred in episodes or programs, and this JFK 2000 redevelopment project was very typical of those episodes or programs. In any event, this late 1980s usage of the cone penetrometer is believed to have been the first use of the cone at Kennedy Airport. Earlier in this century, there were 12 piezocones and 15 seismic piezocone soundings performed for a single terminal project within the central terminal area. Now, the identity of this project and the specific location within those 8 locations I showed you previously will have to remain confidential, because this was a condition imposed on me by the terminal owner, project owner, in order for me to use these data for research purposes. It's essential to note that I had no involvement with either project, either in the late 1980s or this century, and I have received no compensation of any kind from the project owners or project participants, design engineers, construction contractors, material suppliers. That having been said, in the interest of full disclosure, I was a Port Authority Engineering Department employee between 1972 and 1974. And in fact, that's where I first got my start learning about Kennedy Airport. Literally from my first day of employment with the Port Authority beginning in June 1972, I was assigned to a project at that time that was actually looking to bring rail access to Kennedy Airport. And again, in the interest of full disclosure and transparency, there's been no quid pro quo for the use of either set of data that I'm using in this presentation segment. So as I noted earlier in this presentation, all the results I'm going to show you are based on published empirical correlations or using well-known theoretical relationships. For example, shear modulus is equal to total density times shear wave velocity squared. Again, all calculations and plots were done using Excel. So in principle, everything I'm going to show you can be reproduced by any geoprofessional. There's nothing proprietary or magical or mysterious in anything that I'm going to show you. And that's a very important, I think, to appreciate that everything I'm going to show you in this segment is doable in the present by any experienced geoprofessional. These are things we can be doing now. This is not just something that could be done in the future. I decided that the most efficient way to present this information was to take one representative seismic piezocone sounding that was performed for this recent terminal project earlier in the 21st century. And I chose this specific piezocone because it's very representative, and there was some additional information obtained nearby to correlate with it that I think is useful and interesting. But I'll justify use of this particular sounding in a minute. So I'm going to focus on this one sounding to show you what is achievable using the basic QC, FS, and U2 data that you get from either a piezocone or seismic piezocone, as well as to clearly identify what additional unique information can be gotten only from a site-specific seismic piezocone sounding and the shear wave velocity data that it produces. So I'm going to present these results in groups of soil properties and parameters that have the same basic theme or objective, beginning with the results that are obtained from using only the basic QC, FS, U2 data from either a piezocone or seismic piezocone. And then I'm going to follow this up with what additional results you can only get from shear wave data from a seismic piezocone sounding. Note that you can use these empirical relationships with older CPT soundings that did not have any pore pressure measurements for cases where the soils are predominantly coarse grain in nature, and it can approximately and reasonably be assumed that the U2 is equal to the static water pressure U0. Now, I've done this successfully using the 12 CPTs that only had QC and FS data that were performed at Kennedy in the late 1980s when I did my earlier taper pile research related to Kennedy Airport. And I'll justify later on making this assumption. Note also for these older CPT data that QT, the corrected tip resistance, is equal to QC, the uncorrected tip resistance, because there's no pore pressure sensor on the original CPT. So, as I noted previously, a piezocone or seismic piezocone, you take these pore pressure measurements at the U2 location at the shoulder, and because there is now a little bit of water pressure pushing down, you have to correct for that, for the water pressure versus the water pressure pushing up. Well, with the original CPT, there was no pore pressure sensor, nothing on the shoulder, so there is no correction that is required. This QT-QC correction for terrestrial cone soundings, such as at Kennedy Airport, the correction is almost negligible. Where this does become very important is if you're doing a cone sounding in open water. Then this correction of for the pore pressure measurement location becomes very, very important for open water cone soundings. Well, to give you an overview of things, as I said, the format of this presentation segment is an in-depth focus on the calculated site characterization outcomes, the post-process data for one representative seismic piezocone from this recent 21st century terminal project. Now, I will be making selective comparison to other seismic piezocone soundings, as well as other in situ testing methods that were used on this same terminal project, in order to highlight various topics that are quite important and relevant to site characterization. However, before we launch into this detailed discussion, I think it's useful to give you a general indication of the subsurface and surface conditions within the Kennedy Airport Central Terminal area, as well as the range of outcomes from the 39 cone soundings that I've obtained over the last 35 years and used in my various research projects. So this is just a brief synopsis of information that I presented in much greater detail in my 2014 white paper, as well as the earlier 2020 YouTube presentation on Kennedy Airport in general. So I just want to present enough information so you get a basic idea of appreciating the various soil strata we're going to be talking about. So as I've already noted, the Kennedy Airport Central Terminal area is within an area that was occupied by marine tidal wetlands and tidal creeks prior to airport construction, although there had been that localized prior development at Idlewild Point, as well as for the golf course that I noted earlier. So again, just to refresh everybody's memory, these locations were noted earlier in this presentation, and as well as discussed in detail in the 2014 white paper and 2020 YouTube presentation I have referred to. So again, just to remind everyone, there had been this prior development at Idlewild Point and the Idlewild Beach Golf Club before the airport was constructed. And here's the CTA where all of the cone penetrometer soundings I'm going to be talking about were obtained. So these were all pretty much on land. None of them was in a former open water area within Jamaica Bay. And again, to superimpose a relatively present day photo, and this dashed blue line, this is approximately the original shoreline. So this gives you an idea of the portions of Kennedy Airport that were once open water within Jamaica Bay versus being part of the marine tidal marsh area. And again, here's that boot-shaped feature of Idlewild Point, and here was the Idlewild Beach Golf Club. And again, just for historical purposes, the original Kennedy Airport terminal in 1948, when the airport first opened for commercial service, as well as the original control tower, were in this area up here. Right? This was the original location, obviously long since replaced by several generations of other terminals, but the original terminal location and tower location was up here. Here's the present day tower, in case you're curious, right down here by Terminal 4. This is now called Terminal 4. This was the location of, when I worked for the Port Authority, this was the so-called International Arrivals and Departure Building, used by dozens of small airlines that only maybe had 1 or 2 flights a day into Kennedy. So here's the present day tower. For those of you who have traveled through Kennedy Airport or familiar with it, this is the tower locations here. In any event, the overall Kennedy Airport site in the scheme of things is relatively flat. The ground surface elevations at the 39 cone penetrometer sounding locations that I've evaluated vary at most by about 6 feet or about 2 meters. And the average surface elevation is about plus 11 feet, plus 3.5 meters. And this is relative to the 1988 North American vertical datum. Elevation 0 in NAVD 88 very, very, very roughly is mean sea level, just to give you an idea of what the reference elevation is for this. And as I noted, the tidal range within Jamaica Bay is typically, let's say for discussion purposes, about 2 meters, maybe 6 feet plus or minus a little bit. Now, most of the soundings of these 39 soundings were performed to a depth of about 100 feet or 30 meters below the ground surface, although some of the 1980 soundings went a little bit deeper. But for the most part, they were entirely within the upper glacial aquifer. I've had a chance in my professional career to review hundreds of conventional borings that were done within Kennedy Airport. These were all with standard penetration test sampling. And these borings indicate that within Kennedy in general and the central terminal area in particular, the subsurface conditions are relatively uniform in horizontal direction. So here's a typical geologic profile that I showed in my 2020 YouTube presentation. This is very representative of conditions within Kennedy, especially within the central terminal area. See the Holocene sand fill stratum, the Holocene organics, the upper glacial aquifer, which we now recognize as 3 separate formations, Belmore, Wantaw, Merrick. Now, by and large, the Wantaw Formation, which is an old organic clay stratum, is generally absent within Kennedy Airport. At most, it's very thin. And by very thin, I mean perhaps a few inches or a foot, something like that. Something of a few tens of millimeters. This stratum did not show up in any of the cone penetrometer soundings I have reviewed. Where I have seen it is by happenstance that it was found in some of the older borings I've looked at, conventional soil borings at Kennedy Airport. So for all practical purposes, this stratum is not relevant, or this formation is not relevant within most of Kennedy Airport. So really we'll be dealing primarily with the Belmore and the Merrick. Also, the interface between the upper glacial aquifer and the Gardner's clay, as it's called, which is also a Pleistocene formation. The depth of this interface varies. As I indicated earlier, that this is typically maybe around 125 feet or so, perhaps 40 meters or so below the ground surface. Some of the deeper conventional borings I've seen at Kennedy Airport, the last sample or two has wound up in this Gardner's clay. This is a very, very stiff, silty clay. But the focus will be on the 4 strata that I've indicated here with colors. Although conditions are relatively uniform because cone penetrometer soundings provide so much more data, we now appreciate that there is some not insignificant spatial variation in a horizontal direction, certainly more than we used to think about historically. Okay, first we're going to look at the corrected tip resistance QT. And what we're looking at in these plots, we're looking at QT in megapascals versus elevation in meters. And on this plot here, we see the aggregate results of the 12 CPT soundings that were done in the late 1980s, where the data were sampled every 1 foot or 300 millimeters. And over here we see the aggregate results of the 27 piezocone and seismic piezocone soundings that were done earlier this century for the one terminal project, where the data were sampled every 50 millimeters or 2 inches. And the point I'm trying to make here is that while certainly both sets of data are very similar, and the trends within a set of data are very similar, that there are not insignificant variations. And we really see this very clearly with cone penetrometer soundings compared to SPT N values, simply because we have so much more data. So while the results within the central terminal area at Kennedy Airport are reasonably uniform in a horizontal direction, the point I will make later on is that there are enough variations that we need to consider them, the variations typically on a project. And these are the various strata that I'll be discussing in some detail, superimposed on the data points. This is the hydraulic fill, which again is the Pleistocene sand that was dredged from within Jamaica Bay and pumped and deposited hydraulically on the wetlands to create the airport property. Here's the Holocene organics, predominantly organic clay, and the two formations of the upper glacial aquifer, Belmore and Merrick, that appear within the central terminal area. None of the soundings that I reviewed showed the Wantoff formation, or 20-foot clay as it was called in older publications, that very old organic clay stratum that appears very sporadically in borings elsewhere in the airport. These are the same data, but superimposed in the dark black line is the one seismic piezocone sounding from the recent terminal project that I've selected for detailed study and presentation throughout this presentation segment. And I'm just showing you that the particular size piezocone I selected, I feel is quite representative not only of the other 26 soundings on that project, but also quite representative compared to the older soundings from elsewhere within the central terminal area. Well, considering next the friction ratio, R sub F, and expressed as a percent, which is just the sleeve friction divided by the corrected tip resistance and expressed as a percentage. Again, we have the data from the late 1980s and from the earlier this century. The aggregate data plotted versus elevation in meters. Also shown on here in the brown line is at RF equal 1%. This is very commonly used as an approximate dividing line between coarse grain and fine grain soil. So I'm showing this because you'll often see this used in practice as kind of a crude indicator of, as I said, coarse grain versus fine grain soils. And again, here are the Holocene fill, Holocene organics, and the two components of the upper glacial aquifer superimposed upon these data. And again, I'm just showing you the same data, but with the heavy black line being the seismic piezocone from earlier this century that I selected for detailed study. And again, this is just to show you that the specific seismic piezocone I selected, I think, is quite representative of the data, not only from the same project, but also for elsewhere within the central terminal area. Well, now we want to start getting into the heart of this presentation segment, where we're going to be talking about calculated site characterization outcomes in a very, very detailed, granular level. And First going to discuss the basic data that we get from seismic piezocone and piezocone soundings and post-processing for normalization. And let's start off with tip resistance. And what I'm showing you here for the one seismic piezocone that I selected, this is the measured uncorrected tip resistance, QC. This is what you would get from the actual sounding itself. Here's the corrected value. And again, for terrestrial soundings, the difference is really negligible, but we do this anyway. It's easy enough to do, certainly on a spreadsheet. Where you will see a bigger difference is for a sounding that is done in open water, where we have much larger water pressures to deal with. And this is QTN, which is nowadays probably the most common, most popular normalized value of tip resistance that we use. And again, as I discussed earlier in this presentation, the reason for doing normalization is that we remove some of the effects of overburden stresses from the calculation. So we're able to see trends much clearer. This is a parameter that has become very popular in recent years. It's called the normalized clean sand. It's QTN-CS, clean sand equivalent. This is basically QTN as if the soil were a clean sand. And the relevance for using a parameter like this will become clear as we get into this presentation segment. So this has become a very, very popular parameter to calculate these days. And here we see our four strata superimposed on things. And you begin to see the differences here in the upper glacial aquifer, which historically, certainly in the early decades of Kennedy Airport, was all considered to be the same stratum. This is where we really begin to see the fruits of the labor of modern geological research, where we appreciate that there are distinct formations within the upper glacial aquifer. And these really show up very, very well in cone penetrometer soundings. They really, trust me, they do not show up as clearly from SPTN values. And we could see this very clearly in the trends of the tip resistance. Much more uniform within the Belmore formation. We get down here into the Merrick, very characteristic at Kennedy Airport Central Terminal area to have this very, very, very dense layer show up here. Next, we're going to look at sleeve friction. And again, this is the measured value, the friction ratio. And again, I'll show the 1% that is very often used as the dividing line between coarse grain and fine grain. And the normalized sleeve friction that we use widely these days, capital F sub R. And although I have not seen people suggest that we should use a percent to divide between coarse and fine grain, I think you could see that that 1% criterion probably would apply here pretty well also, but I've chosen not to show it. And here we see the strata superimposed. And with sleeve friction, this is where you're going to tend to see differences with fine-grained soils. Fine-grained soils tend to have much higher RF and FR values compared to coarse-grained soils. And again, we see certainly with the friction ratio and the normalized friction ratio, we see very distinct differences between the Belmore and the Merrick. This having an even lower RF and FR value, indicating coarser sands and gravels compared to the Belmore formation. But we see the Holocene organics standing out quite clearly. And now we want to talk about pore pressures. And what we're looking at here, here's the measured U2 water pressure. This is one of, there are many normalized water pressures, but two in particular I have found quite commonly used. This is capital U, which, as you see here, we are subtracting the static water pressure from the measured water pressure to get a net value, and we're also dividing by the vertical effective overburden stress to get a normalized dimensionless value. Another normalized value, BQ. BQ is used very, very commonly with fine-grained soils, which are not predominant here at the Kennedy Airport CTA site, but certainly many other sites, the BQ data would be much more important. And in all three of these plots, the solid light blue line is the static water pressure. And here we notice in the Holocene fill that the measured data are offset from the static water pressure. And that reflects the fact that in general at Kennedy Airport, the piezometric levels within the Holocene fill and the upper glacial aquifer in general are not the same. The Holocene organic stratum is not a perfect aquiclude or aquitard. So the difference in piezometric levels between the Holocene and the Pleistocene are inconsistent. This is one of the higher differences I've seen in the central terminal area. Okay, this indicates that there's a perched groundwater table within the Holocene fill at this particular location of almost 2 meters, 6 feet. So this is one of the larger ones I've seen. But we do find that in general, there is a perched water condition in this Holocene fill. And that's because the upper glacial aquifer that historically was an unconfined aquifer in many areas is now a confined aquifer, certainly in this case due to the presence of the Holocene organics. Here we see the results for the Holocene organics. Again, parameters such as U and BQ are really, BQ especially, very important for fine-grained soils. And here we see the results in the upper glacial aquifer, the Belmore. And I do want to point out, notice here that U2 is approximately equal to the static water pressure. And I'm highlighting this because, as I indicated earlier, that in my research related to tapered piles at Kennedy Airport, I routinely made the assumption when using those older 1980s CPT data that U2 was equal to U0, so I could use some of the newer correlations. And because all of my research involving tapered piles involved this stratum, as you could see, that was a very reasonable assumption to make. It is not, however, a reasonable assumption to make in the Merrick Formation. And here where we see some pore pressure reductions and negative values in normalized pressures, this is very indicative in a coarse-grained soil. This is very indicative of very dense soils where we get dilative behavior and we generate trends towards negative pore pressures. Again, conventional borings do not differentiate between the Belmore and Merrick historically, but we really see the cone penetrometer really brings out the difference between these two formations within the upper glacial aquifer very, very clearly. Well, this now brings us to a very significant discussion, and that is about soil identification and this trend towards using soil behavior categorization. And I'm going to be spending a lot of time on this particular topic because this is one of the very important trends that I mentioned earlier in this presentation, and people may not be fully aware of this trend towards soil behavior type. And as we'll see, there have been a lot of changes occurring within fairly short periods of time with regard to soil behavior type that people may not be fully aware of. So we're going to go through this particular topic in quite a bit of detail and fairly slowly. For most of the 20th century, during the early decades of development and evolution of the cone penetrometer, the primary goal was to develop empirical correlations between the basic tip and sleeve friction data and conventional soil identification that, as we know, is based on soil particle size and plasticity. This is a logical extension of what we do with conventional borings and soil sampling, where we take physical samples of soil, we subject them to visual manual identification in the field and laboratory, and then follow this up by index property testing in the lab, sieve analyses, Atterberg limits, hydrometer, whatever, in order to complete the soil identification process. So cone penetrometer soil ID correlations went through several stages of development, really beginning with the development of the so-called Begeman cone with the friction sleeve, or as I noted, is also called an adhesion jacket, in 1953. It was really the development of the friction sleeve in 1953 that opened up a lot of possibilities. And here we see a typical correlation between tip resistance, frictional resistance, and trying to identify the soil, even going so far as to try to identify the percent of clay minerals. You're likely to see the Robertson and Campanella correlation of 1983. This is probably the best known of the later generation of these soil ID correlations. I think this is when soil ID attempts were at their zenith. And you see again correlations between tip resistance and, in this case, the friction ratio. This FR is, don't confuse this with normalized friction ratio. This is really capital R sub F in modern notation. Before I leave this slide, I just want to point out, notice the units here for tip resistance or bars. This is a very, very common unit you see in, especially in European literature from the early days of the cone penetrometer. 1 bar is 100 kilopascals. It's equal to 1 atmosphere. In imperial units, of course, that would be 14.7 pounds per square inch, or a little bit more than 2,000 pounds per square foot. So this is a very common unit that you see used for stress in early publications, especially from European authors. But you see the power of this is that these correlations were usable with the older CPT cones that only measure tip resistance and sleeve friction. Well, as I've noted earlier in this presentation, in recent decades, the trend has been away from traditional soil identification to what is called soil behavior type. And Dr. Robertson really has been at the forefront of this. He's been the primary proponent of soil behavior type concept. And this is based on a very logical premise that the cone penetrometer is better suited for defining soils by their geotechnically relevant mechanical or performance-based characteristics. That is, defining soil as how we use it in geotechnical and foundation engineering. So this focuses on volume change and drainage, as opposed to the physical characteristics of particle size, gradation, plasticity, as with conventional site characterization based on physical soil samples and laboratory testing. So if you think about it, given that in geotechnical and foundationeering practice and research, it's really the mechanical performance-based aspects of soil that are of greatest interest, the soil behavior type concept is arguably much more useful than traditional soil ID. Now, Robertson first proposed the soil behavior type concept more than 30 years ago, so it's no surprise that it's gone through several iterations and modifications. So it's very, very important to clearly indicate or identify which particular version either you are using or to identify what some author of some publication you're reading is using. This cannot be taken for granted. I really can't emphasize this too strongly, as in my experience, the terminology and notation with respect to soil behavior type can be a little bit sloppy. Authors are not always rigorous about or even consistent in published works by the same author about using consistent notation and terminology. The original version of the soil behavior type concept was introduced in the 80s before the piezocone was in widespread usage, so it was only based on tip and friction from a CPT. The original version had 12 what we call zones of different soil behavior categories. However, this evolved to and settled on a 9-zone categorization that you still see in widespread use to the present. So this is the type of 9-zone soil behavior type chart you'll very often see. And here is tip resistance, and here is sleeve friction, in this case expressed as friction ratio, with the appropriate 9 zones described here. For reasons that will be clearer in a minute, this original 9-zone version is what we nowadays refer to as a non-normalized soil behavior type categorization. Later versions of the soil behavior type concept use normalized cone penetrometer parameters. So as I've indicated earlier in this presentation, we now normalize parameters much more these days. So this has resulted in a normalized soil behavior type that is usually, but not always, labeled SBTN, the N meaning normalization, to distinguish it from the original SBT. This is one area where you will see notation not always used correctly. I have seen normalized soil behavior type charts referred to as SBT, so it can be a little bit tricky for someone who's not used to working with these till you get used to it. So the original normalized chart maintained the 9-zone categorization, and again you see tip resistance and you see sleeve friction. However, if we compare these SBT and SBTN side by side, you see that here's tip resistance, but here is normalized tip resistance, QTN. Again, here is the friction ratio, R sub F. Here is the normalized friction ratio. So these two charts look very similar. Again, 9 categories, very similar descriptions here. But the very important change here is this is based on normalized parameters, which, as I've indicated earlier, is really the standard nowadays. One new feature of the normalized soil behavior type charts is a parameter called the normalized soil behavior type index, I sub C, with I sub C being the approximate dividing line between coarse and fine grained soils. And here you see the 2.60 line here, and I've highlighted the change between zones 4 and 5 where we had the transition of soil types here. I mean, so we still use verbal descriptions of soil type, but we don't get hung up on, using things like coarse to fine sand, etc., that we have used in the past with traditional soil identification. Now initially this index I sub c was based on a version of the normalized tip resistance that you see variously called Q, QT, QT1, sometimes with a lowercase q. As an aside, unfortunately, one of the things about using the cone penetrometer is that you will see a lot of variation in notation, different terminology, different notation used for exactly the same parameter. So unfortunately, it can be a little bit confusing until you have worked with this for some time and clearly understand what is going on. Now, more recently, Robertson proposed a modified normalized soil behavior type index, I sub Cn, that is based on QTn, not QT1. And this introduces a dimensionless exponent n. And we can see the difference between the original QT1 and QTn. Again, these are both normalized, but a little bit, QTn is a little bit more complex in that it allows this exponent here, instead of being set to 1, it allows it to vary between 0 and 1. And this is really done to enhance the power of using this normalized tip resistance. So QTN is really the most common normalized tip resistance we use nowadays. Now, calculating ICN takes a bit more computational effort compared to IC. It requires an iteration process because of an interdependency between QTN, this parameter n I've shown you here, and ICN. But this is trivial. I mean, if you spreadsheet or other calculation software dealing with an iteration that converges very quickly is not a big deal. Again, unfortunately, publications, even by the same author, are not always clear and consistent with notation. So lately, I've seen cases where the notation ICN is used, yet what is intended is clearly ICN. So the bottom line is we should always be using this modified normalized soil behavior type index, ICN, nowadays in calculations. As noted by Robertson, the biggest difference between IC and ICN tends to be for coarse-grain soil. So fortunately, Kennedy Airport provides us a good case history opportunity to look at this difference, and I will illustrate this later on in this presentation segment. Now, it's important I'm spending a lot of time discussing IC and ICN because they've emerged as key parameters for interpreting and post-processing cone penetrometer data, not only in their own right for defining normalized soil behavior type, but for their use in empirical correlations for many soil properties and parameters. So you will see, and we'll see this in a bit, ICN used by itself for different purposes, and ICN is also embedded now in many empirical correlations for soil properties and parameters. So evaluating, I think preferably ICN, and that has clearly been Robertson's recommendation for well over a decade now. Evaluating ICN really has become an essential mission critical step in cone penetrometer based site characterization and post-processing of cone penetrometer data. So the most recent evolution of the normalized soil behavior type concept focuses more explicitly on mechanical behavior. It is broadly divided into 4 quadrants. And these quadrants are defined by dilative versus contractive volumetric behavior and drain versus undrained drainage behavior with a transitional zone in between. So here we see a generic version of the original 9-zone chart marked up with the new divisions. We see the dilative behavior and the contractive volumetric behavior divided by this curved black line. And we see the drain behavior that is also variously referred to as coarse-grained or sand-like, and the undrained behavior that is variously referred to as fine-grained or clay-like with the transitional zone. So here we see the 4 quadrants and the transitional zone. So in the process, the number of behavioral zones has decreased from 9 to 7. We have 2 zones for sand-like, 2 transition zones, 2 clay-like zones, plus an additional clay-like zone for contractive sensitive soils down here, this CCS block we see. So while you do see a lot of people still using the 9-zone version of the chart, I'm going to go with the 7-zone version, which, as you see, has been around for the better part of a decade now. So I think it's time that we all start to transition to using this 7-zone version of the chart. I'm now going to go through this and apply it specifically to the exemplar seismic piezocone sounding from the central terminal area of Kennedy Airport to see how this is used in practice. So this is the results from the piezocone, seismic piezocone I've been focusing on, and we see the 7 zones and we see the 4 strata that we've been discussing. A more useful way of portraying the data, and again here's just a blank generic version, is to look at individual data points or clusters of data points. So here's a simplified geologic profile based on the seismic piezocone sounding we've been discussing. And I want to note that, as I pointed out earlier, we have about a 1.8 meter, almost 6 foot perched groundwater condition in the Holocene fill stratum at this particular location. In general, the groundwater table in the Holocene fill is a perched water table relative to the piezometric levels in the upper glacial aquifer. But this is one of the larger differences I've seen at the airport. These vary quite a bit from location to location, which is not surprising given all the construction that has gone on, past and present. This Holocene organic stratum is relatively thin. As you can see, it's about 2 meters, so maybe 7 feet or so in this location. It's not a perfect aquitard. This has been compromised by countless thousands of piles being driven through it. So you do find quite a variation in the perched water table in the Holocene fill relative to the upper glacial aquifer. So first, looking at the Holocene fill, we see that all the data points cluster here. And you see how this diagram is used in practice. You could see data from a given stratum, how it clusters together. In this case, all falling within the sand-like dilative quadrant. Moving on to the Holocene organics, you see that they plot in the transitional zone. And this is not uncommon in my experience with organic clays, at least in the New York City waterways. I've had a lot of experience, very different sites, not only at Kennedy Airport, but in the Hudson River, many waterways in the New York City area. And what we call organic clay or organic silty clay, just because of the makeup of the material, it does tend to plot more like a transitional material than a true clay. And here we have the Merrick formation of the upper glacial aquifer. You see, again, plotting mostly certainly in the sand-like zone for the most part, mostly dilated, but with some contractive areas. We'll explore this later. and then the Belmore Formation. And if we look at the two formations of the upper glacial aquifer, we can see that on this chart they really do stand out very well. We could see that the data from the Merrick and the Belmore are, for the most part, quite distinctive. And here we plot everything from all four strata together. So these sorts of diagrams are very useful, I found, in practice, to seeing how the data for different strata you may have at a job site or a project site, how it clusters together. These are very, very useful diagrams. And again, notice we're using the QTN and the FR, the normalized values. So in summary, I strongly recommend that you use the 7-zone version. As I said, it's been around for the better part of a decade now, although you still will see a lot of people continuing to use the 9-zone version. But this 7-zone version is much more informative in terms of segregating volumetric behavior, dilative versus contractive, as well as drainage behavior from drained to undrained, with a nice transitional zone in between. Well, I want to continue moving through our topics. Next, we're going to discuss index properties. And I've shown two properties here. One is the total unit weight. And this is an example example of a material property, soil property, where I tend to use an average of several empirical correlations. For some of the soil parameters, soil properties, you find that there have been two or more empirical relationships that are still in use. And I find for something like that, I tend to gravitate towards using an arithmetic mean or just a simple average of the different correlations. And in general, I think the total unit weight forecasts tend to be fairly reliable. Less reliable are the correlations for natural water content. I've had a number of opportunities in both coarse and fine-grained soil to compare the forecast natural water contents from cone penetrometer data to actual laboratory measurements. And in some cases, you get excellent agreement. In some cases, the agreement is poor. I would say here, from my experience at Kennedy Airport, these data are probably pretty good for the coarse grain strata. I think for the Holocene organics, these values are just much too low. So if you use natural water content data, you should do it with caution, or certainly compare it to site-specific laboratory tests, which are easy enough to do. You can do those on split spoon samples. Moving on to fluid flow. The most general cone penetrometer-based methodology for fluid flow properties and parameters for all soil types is the correlation between the normalized indexed ICN and the coefficient of permeability K. Separately and in addition, you could do a physical test called a PPD, or pore pressure dissipation test. And this is done by stopping the cone penetration at some arbitrary depth. And then the technicians simply monitor the variation of the U2 pore pressure until a steady state value, which theoretically should be the static water pressure at that depth, is reached. These PPDs are geared primarily for giving you site-specific values of the coefficient of consolidation in fine-grained soils. You can convert the data to the coefficient of permeability. I've found, and I think a lot of people have found, that the pore pressure dissipation in coarse-grained soils is typically too rapid to be measured with sufficient precision. So although people will do PPD tests in coarse-grained strata, and they certainly were done at Kennedy Airport, my personal experience are that the outcomes are not very reliable or useful. So as I said, there were several PPD tests that were done on the seismic piezocone that I've been focusing on, as well as on the project in general earlier this century from which this came. But I'm only going to show you the outcome from one test that was done within the Holocene organic stratum. That was the only one that I felt was reasonable. So here we have a plot of several parameters, starting off with the coefficient of permeability. And I've reversed the scale here to go from high to low. This is the reverse of normally the way you see it plotted up, because I wanted the qualitative shape of the data to mimic the other two parameters I'm going to show you here. And by the way, I should have mentioned this much earlier in the presentation, but I'll mention it now. One of the things you have to decide when you are post-processing and plotting results from penetrometers is whether to portray the data as individual data points, as I've done with these plots, or as continuous curves. In practice, you tend to see people plot things as continuous curves. I like to do it actually both ways, and then certainly with Excel, it's easy enough to do. You create a plot, and I actually have two plots, one on top of the other on my tabs, one continuous curve, one individual data. Part of the problem and with continuous curves is that when you have variations in data, for example, if this were a continuous curve, you'd have a curve that would go from here to here. Well, what does that mean? Do I have a piece of data here and a piece of data here, and the software just filled in a line in between? Or do I have a string of data as actually occurs? So I'm not saying that plotting continuous curves, which seems to be the more common. If you look at various publications, you'll see that most authors like to plot continuous curves of data. So you kind of get this scratchy line sort of appearance. That's not wrong. I just find that it is more insightful to also plot the individual data points, because that way, as in this case, you could see that, okay, I have a more or less continuous string of data. It's not just a piece of data here and a piece of data here with nothing in between. So I like to plot it up both ways, and it's a judgment call. For some properties and parameters, I find the individual data much more insightful. For others, the continuous curve is useful as well. So just pointing out, this is something, as I said, I should have mentioned earlier. And in my other presentations, I know I did, but this is just a matter of personal preference, and I tend to like the individual data points. In any event, so here we have coefficient of permeability, and here we have ICN, and we see that ICN can be correlated with soil types in a broad descriptive fashion. So we haven't abandoned soil ID completely. We just don't get hung up on trying to say I have, such a percentage of clay minerals or something like that. And we have percent fines. Percent fines is another parameter like natural water content that it's hit or miss. I find that the calculation of percent fines is probably reasonable for coarse-grain strata. I think it's my experience a little bit less accurate for fine-grain strata. So looking at our strata here at Kennedy Airport, this is the Holocene fill. Here's the Holocene organics. And I've plotted up this square, this yellow square with a black outline, is where there was a PPD test. And we could see that the coefficient of permeability calculated from that test actually agrees very well with the general empirical correlation that applies to all soils. that is based on ICN. This permeability, when you look at the empirical equation for it, includes ICN. So as I said earlier, not only is ICN used by itself as a standalone parameter, it is incorporated nowadays in many, many empirical correlations for other soil properties and parameters. And then we have our upper glacial aquifer. Well, and now I want to move on to liquefaction screening, and I'm very excited by this. This is one of the major changes from the last time I prepared a PowerPoint presentation for my YouTube channel dealing with site characterization for the Hudson Valley Varve clays at the New Jersey site. This is a relatively recent development where there's been a lot of work, a lot of publication, and I'm very excited about using this. So the concept of liquefaction screening, as I've said, is a relatively new addition to the cone penetrometer-based site characterization agenda. It was developed originally by Drs. Robertson and Main and others for application to sites and problems involving flow liquefaction. But it should, in principle or concept, be useful for sites such as Kennedy Airport that are potentially susceptible to cyclic or seismic liquefaction. And that's the context I'm using it here. So the objective is to provide a first-order assessment of zones of coarse-grained soil that are potentially susceptible to liquefaction based on their inherent soil structure and their propensity for volume change under shear, that is, contraction versus dilation. The thinking is that if you have a stratum that is in a contractive sort of texture, that it is naturally susceptible to liquefaction, whether it's flow liquefaction or cyclic liquefaction, it is susceptible to liquefaction from its current state. So that's really the underlying premise of this liquefaction screening. It's not intended to be the last word. It's basically designed to help a design professional or academic researcher home in on areas that require further study and analysis. So the intent is that in the case of seismic liquefaction, after doing this preliminary screening, you can then follow this by site and event-specific analyses to quantify the potential or safety factor, however you want to express it, for liquefaction. Well, the cone penetrometer is the obvious investigative tool for doing this screening because it provides essentially a continuous soil profile. So you pick up even potentially liquefiable zones of limited thickness. So this leaves open the question of what soil properties or parameters do we use for this liquefaction screening. Now, historically, liquefaction was viewed from the perspective of relative density. I mean, this is a long-standing index property of coarse-grained soils. But the problem with relative density is that it doesn't provide a theoretical basis for numerically saying or giving us a go or no-go threshold value of volume change potential. Relative density is just that. It is a relative density between 0, which is the theoretical loosest state, and 100%, which is the theoretical densest state, but it doesn't give us any theoretical indication of where in between do we transition from contractive to dilative or vice versa soil structure. So we need something else. We need something better. Well, fortunately, that has already been done. And critical state soil mechanics provides that sound theoretical framework for assessing soil structure. That's the nature of theoretical soil, critical state soil mechanics. And this is the very common plot you see of void ratio versus log of effective stress. And this could either be log 10 or natural log. Both versions are used. And essentially, this behavior is assumed to be linear, although it does tend to be curved over a very large stress range, but usually over some limited stress range, the assumption is made that this relationship is linear. And as you can see from critical state soil mechanics, we can have this thing called this critical state line, which is the theoretical boundary between contractive and dilative behavior. So contractive behavior indicates a tendency for a structure to have volume reduction, which is liquefaction susceptible, versus dilative is volume increase, which would not tend to be liquefaction susceptible. So the fundamental soil property from critical state soil mechanics we use is something called the state parameter psi that quantifies in a rigorous theoretical manner the volumetric soil state relative to that which exists at the critical state. Here's the critical state point here. So specifically, psi is the void ratio in some condition minus the void ratio at the critical state. Here, this is labeled CSL. Here I use CS. It's the same parameter at the same mean effective stress. So we're going up and down at the same mean effective stress. So psi has a positive value, that is contractive nature, if it goes up, and a negative value in its dilative state. So in this case, negative is good, if you will. Positive is less desirable. Well, in addition to this critical state parameter psi, various other soil properties and parameters have been developed empirically to try to define contractive versus dilative behavior. As I said, there's been a tremendous amount of research done on this the last several years. And we're going to take a look at most, but not all, of these parameters that are used. So typically what we do nowadays is we look at several soil properties and parameters. And we look for trends where these parameters all tend to agree. And I'll show you an example, very specific example, for the seismic piezocone that I've been using in this presentation. So we can divide things up into, historically, we used to do relative density, but the problem is, although we can use descriptive terms such as loose or dense, and we have ways of estimating relative density. And again, relative density is another one of those soil properties where there are multiple empirical correlations, so I tend to use an average. But it's unclear from here, what's contractive, what's dilative. There is no theoretical relative density to tell us that. Fortunately, as we have the state parameter, which gives us a quantitative assessment of dilative contractive, and that is a value of 0. So a value of psi equal to 0 defines the contractive versus dilative. However, in practice, people tend to use a value of minus 0.05 as being the transition between contractive dilative. So basically anything less than minus 0.05 or positive is considered contractive. We have a number of qualitative parameters. We have the 7-zone normalized soil behavior type, which inherently gives us contractive versus dilative behavior. We have the normalized clean sand normalized tip resistance, which is applicable to coarse-grain soils, only of course. And based on research, a value of 70 has been proposed as defining contractive versus dilative, although more recent research by Dr. Robertson suggests that there's a bit of a transition going from 70 to 80. So less than 70 is clearly contractive, greater than 80 is clearly dilative, a little bit of a transition. So 70 is certainly a conservative value to use. We can actually use a ratio of soil unit weights, total unit weight to the unit weight of water. And again, a value of 1.8, dimensionless value 1.8 has been found to be a dividing line between contractive and dilative. And finally, the yield stress ratio. We can calculate the yield stress ratio from the critical state line. That's the brown dots you see here, which is a value typically around 3. Okay, so if the yield stress ratio, formerly known as the overconsolidation ratio, is less than 3, then we have potentially contractive behavior. So how do we use this in practice? Well, here's our coarse-grain strata at Kennedy Airport for the seismic piezocone that I've been focusing on. And I'll just take one of several examples. Here we have a zone within the Belmore Formation where we're clearly less than minus 0.05. Contractive behavior based on the SBTN chart. Less than 70 based on the clean sand QTN-CS. A unit weight ratio less than 1.8, and certainly a yield stress ratio that's close to 1, and certainly much less than the critical state yield stress ratio of about 3. So here's a very typical example of where, using a variety of rigorous quantitative as well as qualitative parameters, I think we could conclude with some fairly high reliability that this is a zone of contractive soil that is potentially liquefiable. And without highlighting others, I think you could see that there are other places where the data incur into the contractive zone, right here, 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 here. Now, of course, as we get deeper, as we know, the potential for seismic liquefaction tends to increase. So in practice, we would be looking at the shallower zones. For example, here at Kennedy Airport, certainly one of the zones we very often find is right under the organic stratum, the upper part of the Belmore Formation of the UGA. We tend to have fairly loose soils. We see that here. All right, so this is how you would use the liquefaction screening in practice. Before leaving this slide, I just wanted to point out one thing. I have not seen anybody do it. Perhaps they have. I just have not seen it publicized. Doesn't mean it hasn't been done. But it might be possible to use relative density by developing an empirical value to divide between contractive versus dilative behavior, in the same way that we've come up with 70 here and 1.8 here. We might be able to come up with an empirical value. And at this particular site, for this particular cone penetrometer sounding, relative density of about 50%. All right, notice here for the zone we've just been talking about, clearly it falls below 50% relative density. So it might be, I'm not saying 50% is the correct number to use. This will take a lot of research looking at many cone penetrometer soundings from many sites. But I think it might be possible to come up with an empirical value. What is kind of interesting, though, is normally, if somebody's talking about, well, relative density, we say, gee, well, it's got to be a loose soil for it to be potentially liquefiable. Well, we see here that 50% is smack dab in the middle of the medium dense zone. So I think we might want to revisit some of these perceptions we have about relative density and cyclic or seismic liquefaction. Well, moving on, working our way through our list of soil properties and parameters, I next want to talk about stress state. Before looking at the results related to stress state, there's two foundational topics I want to discuss to kind of set the stage for understanding stress state. First, because the modified normalized soil behavior type index, ICN, has emerged as a key empirical parameter, it's not only being used by itself, but as part of other empirical relationships. And one such empirical parameter that relies heavily on ICM is the exponent M prime that figures prominently in a lot of Dr. Main's various empirical equations for yield stress. And I do want to point out that yield stress has had many different names and notations over the past century of soil mechanics. Maximum past effective stress, natural pre-stress. Some people use a letter P instead of a sigma. For example, in his publications, Dr. Main tends to use sigma prime sub P as the notation. I like to use sigma prime sub VM, M meaning maximum vertical past effective stress. So we can see for this particular seismic piezocone at Kennedy Airport that here's our ICN variation I've shown you previously, and here's how this M prime parameter would vary. So in this case, it's around 0.72 for the coarse-grain soils, fairly constant, and it tends to be close to about 0.9 for the Holocene organics. So I'm just pointing out that this M prime parameter, which relies on ICN, figures very significantly into stress state calculations. The second foundational topic I want to discuss is that both Drs. Robertson and Main have made clear that the empirical correlations they've developed based on the basic QC FSU2 data that we get from either a piezocone or seismic piezocone sounding, these assume what we can call a normal soil. And various terms have been used for normal soils, these soils that are young or well behaved. Dr. Main has used colloquial terms like hourglass sands and vanilla clays. You can think of the way I like to think of normal soils are they're very simple soils that one tends to use in an undergraduate soil mechanics laboratory for instruction purposes. Nothing that has some exotic or unusual behavior associated with it. So in this context, normal is broadly defined as soils without a structure or microstructure due to aging, cementation, or other natural effects, as well as to relatively insensitive fine-grained soils. Dr. Robertson has done work to define outlier soils with structure using shear wave velocity from a seismic piezocone sounding. And as we'll see this later, this is applicable to all soils. So the point I'm getting at here is that one needs to be careful that a lot of these empirical correlations, especially for stress state, assume normal soils. And I'll show later in this presentation segment that the shear wave velocity from a seismic piezocone sounding is what we use to calculate the small strain shear modulus, Gmax. Now I want to point out that Gmax is the most common or the more common notation we see used in the US. Outside the US, you tend to see this parameter called G sub 0 or G sub 0, however you want to pronounce it. So Gmax, G0, these are the same parameter. The important point to remember from this discussion is that structure in soils is correlated with the stiffness of the soil skeleton, which is what the shear wave velocity measures and the small strain shear modulus reflects. So, and I'll make this point several times before I'm done. The seismic piezocone nowadays is recognized as an essential mission-critical in-situ testing tool for evaluating soil structure. Stated another way, if you're going to use a cone penetrometer at a site, you must do at least one seismic piezocone and measure the shear wave velocity. To me, that is simply a given. It's a necessity. It's not a luxury. And I can't emphasize this enough. I've worked with a lot of geotechnical engineers who tend to view the seismic piezocone as a luxury and not a necessity. And I've had colleagues say to me, well, you know, I'm not going to use the seismic piezocone. We only use that for earthquake analysis. Nothing could be farther from the truth. I'm going to show you numerous examples before I'm done with this presentation where the seismic piezocone is really essential and mission critical. So if you use the cone penetrometer on a job and you don't do a seismic piezocone sounding, you've just wasted your time and your client's money, in my opinion, because that is the only way to tell if you have soils with structure at that site. And you can't look at them. I'm going to show you very specifically for this terminal site at Kennedy Airport that you can have soils with structure where you least expect it and in conditions that you least expect. Dr. Main has done his own work related to soil structure, primarily focusing on the sensitivity of fine-grained soils, and he uses a different approach based on QCFS and U2 data to define sensitive fine-grained soils. Main uses 3 different equations based on forecasts of maximum past effective stress for evaluating whether a fine-grained soil is behaviorally vanilla, as he likes to call it, or not. And these are his 3 empirical equations. So these are 3 different equations for maximum past effective stress, and based on data from a piezocone or seismic piezocone sounding. Just point out this coefficient has changed over the years in his publications. So for normal, well-behaved, and sensitive clays, these 3 values should be about the same. However, for organic clays, you will have a very distinct hierarchy, as indicated here. For sensitive clays, you get a slightly different hierarchy. As you can see, these parameters simply reverse. This stays in the center. If we look at conditions for the seismic piezocone at Kennedy Airport we've been discussing, I think you could see here that the Holocene organics at Kennedy Airport follow the hierarchical structure one would expect for organic soils. All right? So if these were inorganic, insensitive soils, these 3 sets of data would plot more or less on top of each other. But as you can see, they plot up very distinctly, and they have the pattern, typical pattern for organic soils. If you want to see more about this, Dr. Main and his colleagues have written a number of papers in recent years applying this concept to a wide variety of sensitive clays and organic clays from around the world. So there's quite a bit of published information that is available out there to get into this in greater detail. I'm not going to go farther with this here because the fine-grained soils are really a relatively insignificant factor at Kennedy Airport. So let's look at some of the soil properties and parameters related to stress state. Looking at yield stress, which is the preferred term nowadays for what we used to call maximum past effective stress. These are all the results based on this M' parameter. And you notice that I have 3 different plots. This one is all the data individually, here I have averaged the data over plus or minus 150 millimeters or 6 inches. And here I've taken the median of the data over plus or minus 150 millimeters or 6 inches. Why do I do this averaging and or mean or median calculations? We find that on sites where we tend to have a lot of variability, where if this were drawn up with a solid line, this would be a scratchy line going all the way up and down. Where you have a lot of variability, different researchers have proposed that taking an average or a median is actually the preferred thing to do, that you eliminate some of the noise, if you will, in the data, some of the scatter in the data. Now, we don't have a lot of scatter at Kennedy Airport compared to, if you've viewed my presentation on the Hudson Valley Varve clays for a site in New Jersey, that was a classic site where there's a lot of noise in the data. And I'm going to show you that in a minute for those of you who have not seen that video. So this is why, certainly for certain properties and parameters, I like to calculate these average and median values. Again, easy enough to do with Excel. And here we just have, again, this I've already showed you, this is Maine's fine-grained soil correlation, so only applies to the Holocene organic stratum. So if we superimpose our soil strata on here, we see in the solid brown line is the calculated overburden stress. We see quite a variable estimate of yield stress, especially down here in the Pleistocene outwash strata, the upper glacial aquifer. And this suggests a very complex stress history of many, many episodes of deposition. Perhaps there was some local advance and retreat of the ice margin. We don't know. But we see a rather complex stress history down here. A complex stress history in the Holocene fill, and I think this really represents just human activity over the last 80 or so years that Kennedy Airport has been around. Whereas within the Holocene organics, a much more uniform estimated yield stress. I want to move on to a parameter called overconsolidation stress difference. We rarely see this used in practice. I think this is a parameter we really should be using a lot more, OCD. It's simply the yield stress minus the overburden. And the idea of doing this, and again, here's the just the OCD average and median with our geologic profile superimposed on it. The reason for doing this is that if you had a site where you know that there was some, say, natural erosion that occurred over time, or perhaps human activity that removed a certain amount of overburden soil, this OCD you would tend to see a uniform value with depth if a uniform amount of material was removed over a large area. In this case, we see a much more erratic type of profile, and I think this reflects simply the natural complex deposition of the upper glacial aquifer. But again, I think this parameter we should be using or certainly looking at a lot more in practice. Next, I want to look at the yield stress ratio, what we used to call the overconsolidation ratio. And again, you see I've used both the actual values, the average and the median. And again, just superimposing our strata here. Again, we see a very complex behavior, a lot of overconsolidation in the Holocene fill, and again, this simply reflects, I mean, there's values that are off the chart here. I didn't even show extraordinarily high values. I think this just reflects human activity. Again, keep in mind here in the central terminal areas, terminals have been built, torn down, replaced, built, torn down, replaced numerous times in the 80-year history of the airport. A rather complex pattern of yield stress ratio down here, and this is going to have some very practical implications. I'm going to discuss that at the end of this presentation segment when I give you some of my personal observations. This sort of thing, and keep in mind for coarse-grain soils, this is a type of parameter that before the cone penetrometer came along and the various empirical correlations, this was not something we could ever calculate for coarse-grain soils. We couldn't calculate what the yield stress is. We can't run odometer tests realistically on sands to test what the yield stress is like we can with fine-grain soils. So here we're seeing a lot of stress state parameters that for coarse-grain soils were heretofore impossible to get on a routine basis for projects. So they're very, very powerful results, and we'll see the practical implications of this a little bit later in this presentation segment. Coefficient of lateral earth pressure at rest, KO, and again, the basic value, average, median, and the soil strata. Again, note the variation in KO here in the upper glacial aquifer, and I will talk about some important practical implications of this a bit later. I next want to move on to shear strength. And the cone penetrometer has historically been used to estimate more Coulomb strength parameters, the drain friction angles in both coarse and fine-grained soils, as well as the undrained shear strength in fine-grained soil for use in cases or conditions involving static loading. Much more recently, Dr. Robertson and his colleagues have developed empirical correlations for estimating the residual undrained shear strength of coarse-grained and transitional soils that have undergone flow liquefaction. So the concept of undrained strength, and I had indicated this earlier in the presentation, has been extended to coarse-grained soils. Although, of course, we have coarse-grained soils at Kennedy Airport, flow liquefaction is not a design concern. So I'm not going to be talking about those undrained correlations. If this is something that interests you, I suggest you look at some of the recent publications by Dr. Robertson. It's also discussed in the Greg Drilling 7th edition of 2022, that manual that I mentioned earlier in this presentation. So I'm only going to discuss the drain friction angle under static loading. So what we see here, we see I'm using the correlation of the peak friction angle can be decomposed into a constant volume or critical state friction angle plus a dilatancy component. So here we see plotted in green is the critical state or constant volume angle, which is fairly constant with depth. It's fairly high here, the Kennedy Airport sands, which tend to be quite micaceous. That actually tends to increase the C sub V value, phi sub V value. And we see a lot of variation in the peak value, which is explained by variation in the dilatancy component. In a lot of cases, the dilatancy angle is quite small. In other cases, fairly substantial. What's interesting is the cases where the dilatancy angle is very small are actually cases where we have contractive soil zones. Although I don't show it here explicitly, but this was where I showed you earlier when we were talking about liquefaction screening. This was the zone I highlighted with that purple box right down here. So this is a contractive zone, and we can see that that zone has a very low dilatancy angle. So although I've not seen specific research along these lines, it would appear that perhaps the dilatancy angle might be another interesting way to try to empirically identify zones of coarse-grained soil that are contractive versus dilative. And if we look here, we see that a dilatancy angle perhaps of about 3 degrees, just as a round number, might be an interesting benchmark for identifying. And I think we see that, right? Anything less than 3 degrees, the dilatancy. This is contractive zone up here, right under the organics. Certainly we know this is a contractive zone, a couple smaller contractive zones here. So dilatancy angle might be another kind of indicator, organism, if you will, of liquefaction potential. And finally, just superimposing the different soil strata on our diagram here. Well, I want to move on now to the discussion of soil stiffness and soil structure assessments, and I want to focus on the use of the shear wave data from seismic piezocone soundings. I said it at length earlier, and I'll say it more than once again, that to me, I've become convinced that a seismic piezocone sounding, even on the smallest of projects, is a necessity. It's not a luxury as had been viewed, and a lot of people still view it. So one of the most significant advancements, as well as paradigm shifts in cone penetrometer-based site characterization, has been the ability to measure soil stiffness. What makes this a significant advancement is that stiffness, which we know is an essential aspect of soil behavior for many geotechnical and foundation applications, has always been costly and difficult to measure accurately in the field or laboratory, especially for coarse-grained soils. I mean, we can't routinely take undisturbed tube samples of coarse-grained soils, take them to a lab, and run traxial tests on them. So what makes this a paradigm shift is that the cone penetrometer, if you think about it, is inherently a large strain testing device. All right, because we're pushing this thing through the soil, we're essentially failing the soil to advance the cone penetrometer. By definition, when we measure Q sub C and F sub S and U2, we're measuring this under failure conditions of the soil, right? Under ultimate large strain conditions. So this is really geared to measuring, the cone penetrometer is inherently geared to measuring soil strength. So the ability to measure soil stiffness and to assess soil structure based on aging, cementation, things like that, is a small strain activity. And again, I want to point out that the behavioral age of a soil deposit is not the same as its geological age. There's only ever one geological age. I mean, the geological age of the upper glacial aquifer is the Pleistocene, all right? That's when it was deposited. But behaviorally, it might behave as a Pleistocene soil, it might behave as a Holocene soil. It depends if its structure has been disturbed by some natural or human activity since it was deposited. And I'm emphasizing this behavioral age and soil structure aspect because, as we'll see, it does impact the liquefaction potential. So there's two methodologies for assessing the soil stiffness parameters. We could use the basic QCFSU2 data from a piezocone or seismic piezocone sounding with some empirical correlations, or we could use shear wave data from a seismic piezocone sounding with theoretical equations and empirical correlations. We're going to look at both methodologies. But the point I'm making here, it's essential to understand the underlying basis for each of these methodologies so that you interpret and use the outcomes correctly and in a complementary manner. These are complementary. They're not at odds with each other. This is not either or. You need to use both of these together. And again, I'm going to show you examples of why I'm so adamant on this point. So when you just use the basic QCFSU2 data from a piezocone or seismic piezocone sounding, the stiffness assessments are limited in their applicability because of the assumptions and limitations of the databases that went into developing the empirical correlations. Again, all of these empirical correlations are based on the assumption of the quote-unquote young, well-behaved soil, hourglass sands, if you will, where there is no structure to the soil due to aging, cementation. There is no sensitivity of the soils. The biggest problem, is really a serious issue in my opinion, is that the results from these young, well-behaved soil correlations, and not only do they not cover soils with structure or sensitivity, they don't even identify or flag such soils. So, if you use one of these empirical correlations based on QCFSU2 data, you'll always get a value. You'll always get a number. But you have absolutely no idea whether that number is, yeah, that's actually a pretty good estimate of the real value, or if it's way off base, right? It's not like there's some indication that, gee, look at this number, it's telling me I have soil structure. That's not possible. So again, as I've now said several times and will continue to say, performing a seismic piezocone sounding and using the shear wave data are the only surefire way to tell if you have soils with structure. And I'm going to give you a very specific example for this terminal site at Kennedy Airport that will illustrate why I'm so adamant about making this point. So let's look at the basic results we get from doing seismic piezocone sounding and measuring the shear wave velocities. And again, these are what we call interval shear wave velocities, as I explained to you at the very beginning of this presentation. So what we see here, these are the basic shear waves velocities in meters per second, plotted depth versus meters, in meters for the seismic piezocone sounding that I've been using. All right, so each of these represents an average shear wave velocity over an interval halfway up, halfway down to the next data point. And you can see in this case, these data were obtained at about a 1.5 meter or 5 foot vertical spacing. I've also seen soundings at Kennedy where the data were obtained every meter, every 3 feet. Again, how closely spaced you want to obtain these data, it's how much money you want to spend. Okay, that's really the governing factor. One of the reasons I chose this specific seismic piezocone to focus on in this presentation is that very close to this sounding, there was a conventional soil boring, and in that soil boring, they did downhole primary and shear wave velocity measurements, both receiver to receiver as well as source to receiver. So what you see with the circles are the borehole shear wave velocities that were measured close to this piezocone. And you see, I think there's really very good agreement here. I mean, all of these data points, the red squares from the seismic piezocone and the blue and yellow circles from the downhole shear measurements in a borehole. These pretty much plot on top of each other. So this is pretty good agreement in my opinion. And here, what I'm showing you is, again, the red squares are the measured values. I'm showing you the results from two empirical correlations. The red dots are from a correlation that was published by Robertson in 2012. And the green dots were from a different empirical correlation that appear in the 2022 version of the Gregg 7th edition manual by Robertson and Cabal that I showed you earlier. I've had the opportunity to use these two correlations on many seismic piezocones. I'm a great fan of the Robertson 2012. And you see in this case, the red dots and the red squares, they really correlate. I think the correlation is outstanding. It doesn't get any better than this in my experience. The green correlation, although it's a decade newer, not quite as good. It hits a good part of it, but notice that it misses some of these peaks up here and here. So this is a classic example of something that I talked about early on, and that is there is no unique what's the best best correlation to use. There's a lot of professional judgment goes into it, and newer is not always better. I mean, here you have a correlation 10 years newer. In my experience with using this correlation, at least at Kennedy Airport, it is not as good as one from 2012. So what I do with my spreadsheet, in a lot of cases, I will plot more than one correlation just to see how they compare in a given situation. And again, I'll superimpose our geologic profile. So this is one of the reasons I chose this specific piezocone is that it is a very classic example of a vanilla soil site. Okay, this is here the sands are very vanilla, as Dr. Main would like to say. All right, these soils all behave as though they are young and well behaved. Although young usually means Holocene, and these are Pleistocene soils, nevertheless, they are very well behaved in terms of there's very good agreement with the empirical correlations that were developed based on young, well-behaved soils and the actual measurements. So this is one of the reasons I chose this particular piezocone, as well as the ability to compare it to other types of data as I've done here. Well, let's look at some of the interpreted results for soil stiffness. Here we have the small strain shear modulus G max. Again, a lot of places will call this G naught, and this just comes from a theoretical equation. We know that shear modulus equals total density versus shear wave velocity squared. Now, a lot of people, when they do a cone penetrometer sounding, will simply assume a density. I go a step further. I actually use the calculated total unit weights that I showed you previously. I convert those to a density, and then I use those. But I'll point this out. For example, if some of the commercial software that I've seen, when making this calculation, built into that software, the programmer has assumed that the density of the soil is a fixed number. Is it wrong? No, it's a professional judgment call. I'm not going to say it's right. I'm not going to say it's wrong. It's one of those gray areas of professional judgment. But I like to use the actual density. It's simple enough to do with a spreadsheet. And again, you see, I've plotted both the mean and median values of the shear wave velocity. In calculating density, meaning since these are interval velocities, I take the density over that 1.5 meter zone of soil. And again, the red dots are the Robertson 2012 correlation. This is the reduced rigidity index for coarse-grain soils. The individual data points, this triangle and squares, are for the actual data, and the red dots are for the empirical correlations. And here's the rigidity index for fine-grained soils. Again, these are the measured values, and here are two empirical correlations from the literature. We see for the Holocene fill, we see for the Holocene organics, and then for the upper glacial aquifer. So as I've now stated several times, performing a seismic piezocone sounding and using shear wave data obtained from that sounding are really an absolute mission critical necessity. Again, if you're going to do a cone penetrometer or use the cone penetrometer on a project, you have to do at least one seismic piezocone. If you don't, in my opinion, don't bother using the cone, because the shear wave velocity is the only surefire way to identify the presence of soil structure reliably and to quantify it accurately. And I'm going to show you an example. Now, for this, so far, this case history seismic piezocone I've been using, the correlation between the theoretical results and the empirical results were excellent. And as I've already said, this is an example of a nice, well-behaved soil. However, you should never take this for granted or assume it or extrapolate it, even for the same site or even on the same project. I'm going to show you why in a minute. How do we detect soil structure? All right, I've been harping on it. So, okay, how do we actually detect it? Well, there are several empirical parameters that have been defined specifically for evaluating or assessing soil structure. These are based or crafted around a parameter called the small strain rigidity index, I sub G, and it's based on the site-specific measured value of G max or G naught as calculated from the measured value of shear wave velocity. So here's a generic plot, and here's the small strain rigidity index, which is the small strain shear modulus divided by normalized tip resistance. Here's normalized tip resistance here. And this just indicates a trend of increasing compressibility in the soil, right? The smaller this index, the less stiff the soil as we go from right to left here. Well, this is how the results plot up for the seismic piezocone at Kennedy Airport I've been discussing. And you can see I show you different symbols for the 4 different strata we have, both based on mean and median values of soil density. When we have these plots, we also calculate what we call modulus number, capital K sub G. And the function of the modulus number is to bracket the baseline young or well-behaved values, right? So we see this zone here between the dotted and the solid black lines. These are ideal soils, young, uncemented. And we see those same two here with the dashed and solid blue lines. And all of the data for this particular site, for this particular seismic piezocone, fall within here. So this confirms what I had been saying, that this is a vanilla example, if you will. How do you know you have soils with structure, microstructure, cementation, etc.? They're going to plot to the right of this KG line. Be careful when you review the literature. the empirical equation used to define this modulus number Kg has changed over time. Each definition has different boundary values, and unfortunately the notation is not always consistent. So from one publication to the next, even with the same author, I've seen an inconsistency in notation. So you really need to verify on a publication by publication basis how the modulus number is empirically defined and labeled. And I'm going to illustrate in the following slide. I'll show you 3 different definitions of modulus number for the seismic piezocone that I have made the focus of this presentation segment. So here we have 3 different definitions. I call Kg1, Kg2, Kg3. You can see that they're all variations on a theme, right? They involve the small strain shear modulus, various normalized values. This is just overburden stress. This is tip resistance. So these are all expressing very similar results. Just what has been perceived by researchers as what's the latest and the best has changed over time. Right? Once upon a time, this was the best, then this, and now this one is considered the best. And you can see each one of these has different brackets for Kg to define well-behaved soil. And we see the data from our piezocone, falls in between here. This is the result I've shown you previously. This is from what I could see in the literature, the latest preferred version. And again, here's our soil strata. So this is just another way of showing you, as a function of depth, how do the various soils encountered in a seismic piezocone, do they fall within the boundaries of what we consider well-behaved soil? And again, they do. There are some additional parameters that we can obtain using the shear wave velocity. And these are generally of interest for liquefaction assessments, because we now understand that the age of the soil and soil structure play a role in seismic liquefaction. It makes use of the fact that the tip resistance is a function of large strain soil behavior, and therefore tends to measure the soil strength and compressibility. On the other hand, shear wave velocity is a function of the small strain soil behavior and is strongly influenced by soil structure. So these two things from the same sounding, the tip is failing the soil, therefore focusing on the soil strength, its large strain behavior, and the geophone is set behind the tip where the soil is still relatively undisturbed, so we're measuring the small strain behavior. So we need to develop correlations for these two parameters, QC and VS, because they each focus on a different aspect of soil behavior, and therefore they're not exclusive, they're not duplicative, they're really complementary and synergistic. And we need to normalize these values to remove the influence of vertical effective stress. And again, this is nothing new. We've been doing this for decades with things such as SPTN values. So what are some of the liquefaction-related parameters I've seen people use? Well, one of them is the normalized shear wave velocity. And again, in meters per second. Here we're simply taking the shear wave velocity and we're removing the vertical effect of overburden stress. And the individual data points, the square and triangles, are the measured values, and we see the two empirical correlations, Robertson 2012 and 2022. This is a parameter called Y that we see depends on the shear wave velocity and the tip resistance. And I'll explore this parameter a little bit more in a second. And here's what I think is an interesting parameter. ASF, again, shear wave velocity, tip resistance. See how actually this is ICN that is used here. See how it appears in these empirical correlations. This stage stands for age scaling factor. And this is an interesting attempt to try to estimate the behavioral, not the geological, but the behavioral age of the soil. Holocene, Pleistocene, and Tertiary. And we see our soil strata superimposed here. And this is what we would expect for soils without structure. All right, they're all falling in the Holocene, Pleistocene type of range, which is certainly what we'd expect. Just to digress a bit and mention this Y parameter a little bit more. Again, it's a function of the tip resistance and shear wave velocity. It reflects the compressibility of the soil and incompressibility, which we get from the tip resistance, and also has factored into it the age of the soil, which we see here. And all I'm showing you here is that the values we measured at Kennedy Airport in the seismic piezocone I showed you, they fall in the values that have been observed from other sites. Most of these sites are in North America, either in Canada or the US. Well, that brings us to the last topic in this presentation segment, and I'd like to share some personal observations from having used these empirical correlations for some time now, as well as with some specifics related to the Kennedy Airport site. Compared to traditional soil borings with split spoon sampling, vertical intervals that are typically about 5 feet or 1,500 millimeters apart, and resulting SPTN values that are inherently inconsistent due to variation in the energy delivered during the performance of the non-standard standard penetration test. Piezocone and seismic piezocone soundings provide many more pieces of interrelated high-quality data that are collected using a much more standardized and reproducible testing protocol. In addition, development of the seismic piezocone has allowed for an additional piece of data, the shear wave velocity, to be collected at intervals that, as I've indicated, can be as closely spaced as desired, although certainly we always have to weigh cost versus benefit. To me, the development of the seismic piezocone has proven to be especially a game-changing development, as research has shown that the shear wave velocity provides ground truth about aspects of small strain soil behavior in terms of stiffness and structure that are not inherently provided by traditional cone penetrometer sounding that are dominated by large strain behaviors of strength and compressibility. So I said it before, but it bears repetition in this summary that both QCFS and U2 data, as well as shear wave data, are necessary on every project, no matter what the size, as the interpreted data are complementary because they focus on different aspects of soil behavior, and their combined results are therefore synergistic and mission critical for complete and accurate site characterization. This was a central tenet of my earlier presentation about a small project in New Jersey that involved the Hudson Valley Varve clays, where only one piezocone and one seismic piezocone were performed. Now, with specific regard to the cone penetrometer testing at Kennedy Airport that began in the late 1980s and has since progressed to the piezocone, a seismic piezocone, there really has been a profound impact, I think, on the perceptions and understanding of subsurface conditions at the airport that are relevant to geotechnical and foundation engineering. I want to emphasize practice. This is not just a theoretical exercise. Again, my comments throughout this presentation are really practice-oriented. So this is due to the increase in the volume of data that are provided, the nature and quality of these data, and the breadth and quality of the site characterization outcomes that can be obtained from these data. I've tried to illustrate in this presentation the wide variety and number of soil properties and parameters that we could estimate using piezocone and seismic piezocone soundings. There are three very specific topical areas I want to focus on this in this closing observation discussion that have had a major impact on the understanding of subsurface conditions at the airport that are relevant to geotechnical and foundation engineering. And again, I say this as one who has been involved as a practicing engineer going back to 1972, when we were still doing things with slide rules and nothing more than standard penetration test data. So, I've been around in professional practice going back a long time, going back to the slide rule era, calculators, computers. So I've seen a lot of developments and have seen firsthand how they impact the practice of geotechnical and foundation engineering at Kennedy Airport. The first topic I want to discuss is that, again, while overall subsurface conditions at the airport are relatively uniform over large horizontal distances, for such a large site, again, about 5,000 acres, 2,000 hectares, relatively uniform conditions compared to a lot of sites. The conditions within a range of depth typical for present-day driven piling, which is the foundation of choice at the airport for all types of structure foundations, exhibits relatively significant variation, even within the limits of a single project. And I want to discuss this in more detail at this point. So we can see this for the terminal project was undertaken earlier this century. I've previously shown you this slide. These are the piezocones and seismic piezocones that were done for this terminal project, and we see a fair amount of variation within a site that only varied by a couple hundred meters in either direction. Now, it's interesting to note that for the first 30 or so years of the airport, this was the typical depth for piles. The piles were all creosoted timber. The design loads on these piles are very modest in the scheme of things, and it was not uncommon for these piles to fetch up, if you will, within 5 or 10 feet, 1.5 to 3 meters into the upper glacial aquifer once you pass through the organic stratum. So relatively short, relatively shallow embedments in the bearing stratum. Currently, piles are required to go substantially deeper, as I indicated at the beginning of the presentation. Here I'm putting some numbers on it. Part of the reason, a very important part of the reason, is the desirability to get through strata that are susceptible to liquefaction, which tend to be up here and the shallower portions of the Belmore Formation, as well as for the much higher allowable loads per pile that we use in design nowadays. So currently, the driven piles are substantially deeper the last couple of decades as opposed to what they were in the earlier years at the airport. So this suggests that these project-specific variations should be considered during design and construction, as they can result in some very important, significant variations in design parameters as well as construction outcomes in terms of how deep the piles drive. So what I'm getting at here is I think we need to get away from the temptation to say, well, on a project, I'm just going to use one typical condition and I'm going to design everything based on that condition. You know, the cone penetrometer soundings have indicated that even within a single project site, we can get some relatively significant variation in subsurface conditions that we need to consider that variation and the effect on likely driven lengths of piling, in this case, on the project. The second of 3 points I want to emphasize are that the detailed site characterization assessment using cone penetrometer data, as I've outlined in this presentation segment, allows for an understanding of deep foundation behavior at the airport that historically we have not had available to us. So until recent years, we've not been able to understand why things happen the way they've happened at the airport. And I want to illustrate this in the context of the example seismic piezocone sounding that has been the focus of this presentation segment. Again, this is the depth that timber piles were driven in the first 30 years or so that the airport existed. And if we look at the specific seismic piezocone that I've been focusing on in this presentation segment, I want to look at two soil properties. One is the yield stress ratio and the coefficient of lateral earth pressure at rest, both of which are, of course, intimately related. And again, the timber piles that were driven during the first several decades at Kennedy Airport typically fetched up within the first 5 or 10 feet into the upper glacial aquifer bearing stratum, 1.5 to 3 meters. Unfortunately, because there are still structures at the airport supported on these relatively short piles, this is a zone that is likely to liquefy in a seismic event. But we'll not going to dwell on that point here. What I do want to dwell on is, as we know, for deep foundation elements, the unit shaft resistance is proportional to a dimensionless parameter K sub h, which is a post-installation lateral earth pressure coefficient, times the vertical effective overburden stress. And we can decompose this K sub h into two components. One is the pre-installation value of the coefficient of lateral earth pressure at rest, which we could see is relatively high. All right, you look here, you see values around 0.9, close to 1. So substantially higher than in deeper portions of the upper glacial aquifer bearing stratum of the airport. And these high KO values are the result of relatively high yield stress values that we see here. The second component of K sub h is the dimensionless ratio KH to KO, which reflects the type of deep foundation element that we use and the installation method. And in this case, we use timber piles, which are naturally tapered, meaning the diameter at the head of the pile is larger than the diameter at the toe of the pile, and the installation method, which is conventional impact driving. So rather than the point I'm getting at here is rather than using a single KH value, it is helpful if we decompose it, and this is arithmetically obviously equivalent to KH, we can decompose it into two things. What's the KO value we start with? And this reflects how does the type of pile deep foundation we chose and the installation method we chose, how does it increase the K sub H relative to the pre-existing KO value? And with tapered piles, we have this unique physical mechanism of wedging that I don't feel has gotten the proper attention it deserves. If we look at some arbitrary fixed plane in space in the ground, essentially what it appears to that fixed plane is that as we drive this tapered pile in the ground, the diameter of the pile is increasing. And I call this physical mechanism wedging. And wedging involves the creation followed by additional expansion of a volume relative to a fixed plane in space, an arbitrary fixed plane in space in the ground. And the result of this wedging is an increase in the horizontal stresses, and I show this by ever larger horizontal arrows here. These reflect increases in radial earth pressures acting on the pile until some limiting pressure is reached. So this is, in a way, it's like performing a pressure meter test, right? You install a pressure meter to a fixed depth, and then you expand the bladder of the pressure meter so it increases in diameter until some limiting value is reached. So driving a tapered pile on the ground is like running a pressure meter test, if you will. And for a taper-driven pile, this wedging occurs in two distinct cumulative stages. We get wedging during driving, and under post-installation load, as this pile moves a little bit deeper in the ground, we're going to get an additional increase in apparent diameter and radial stress. As I said, this physical mechanism of wedging that occurs only when we drive a taper-driven pile on the ground is distinctly different from when we drive a constant perimeter pile on the ground. Right, here's the simulated driving of a constant perimeter pile. Once we create the hole in the ground, relative to some depth, arbitrary depth, we don't increase the diameter. It just slides into the ground. Whereas at that same depth for a taper-driven pile, we are increasing the diameter, increasing the radial pressure. So the point I'm trying to make here is that the KH-KO ratio for a tapered pile is substantially greater than that of a constant perimeter pile. And Nordland, this was the heart of Nordland's research 60 plus years ago. Everybody's familiar with the Nordland method for assessing the axial compressive geotechnical resistance of a pile in coarse-grain soil. Coming up with KH over KO values, this was the heart of Nordland's work. And this substantial difference exists under both driving as well as post-installation loading. If you want to learn more about this in more detail, I've written a monograph about tapered piles, and I also discuss a summary of that monograph in a narrated PowerPoint presentation that I have on my YouTube channel. But I want to get back to the point that is more the focus of the current discussion, and that is the important role played by KO, coefficient of lateral earth pressure at rest here. It's both the starting value, it's both a value in and of itself, as well as the starting value for installation of a deep foundation element. So the point I'm trying to get at here is, for decades we knew that timber piles at Kennedy Airport would drive surprisingly shallow depths to get surprisingly high geotechnical resistances. This was literally the very first job I had when I started working for the Port Authority. In summer of 1972, I was out at Kennedy Airport working a night shift doing test pile installation and pile load tests. And everybody from me as starting as an engineer fresh out of school to experienced engineers in the office with decades of experience were surprised at how much geotechnical resistance, because we tested these piles to a geotechnical failure, how much resistance we got at a very shallow depth. And nobody could explain it at the time. Well, we simply didn't have the knowledge we have now. We did not have a way of estimating what KO is as we do now with the cone penetrometer, right? So this is a very, very powerful result, I think. We get results, in this case, stress state parameters for coarse-grain soil that heretofore we've never been able to obtain. And this helps us to explain a lot of things. And conversely, to extrapolate that knowledge to future projects. Third and final point I want to make is about shear wave velocities and why I've harped on the point that obtaining these is a necessity, not a luxury, in every project. And it's simply because they can reveal potentially significant variations in soil structure that would otherwise be undetected. So on the same terminal project at Kennedy Airport that was undertaken earlier this century, that I've used a typical seismic piezocone from, the cone penetrometer soundings revealed a totally unexpected variation between two areas within the same project site. And these two areas were no more than a couple hundred meters apart. And had seismic piezocone soundings not been done and the shear wave velocity data not been interpreted, we would never know this difference existed. I'm going to illustrate this difference on a series of slides. I'm going to look at two seismic piezocone soundings from this project. One I'll call A and the other B. Basically, we're done at the same elevation, so elevation was not a factor here. The surface elevation was only about 1.5 feet, less than half a meter difference between the two areas. And what we found, out of all 15 seismic piezocone soundings that were performed on the project, they either were similar to A or they were similar to B. So these two soundings, A and B, are examples of the variation in soil structure on the project. And by the way, the seismic piezocone sounding that I've used throughout this presentation segment, it fell in the category of piezocone A, which, as we'll see, is the vanilla example. So we're going to see that seismic piezocone A is reflective of young, well-behaved vanilla soils, hourglass sands, whereas seismic piezocone B is not so well-behaved, atypical sands. Well, let's start off with basic data. We're going to compare the green curve is A, the red curve is B. Here I'm showing you the corrected tip resistance and the friction ratio. And I want to focus on this lower portion here of about 12 meters, about 40 feet, the lower portion of these two soundings in the upper glacial aquifer, because this is really the area of interest. And the interesting thing is they're very similar, but interestingly enough, sounding A, the green curve, shows a peak at this depth at about elevation minus 20 meters, a little bit below that we find in a lot of cone penetrometer soundings at Kennedy, even going back to the ones from the late 1980s, but is absent in sounding B. Okay, so this peak is very, very typical of the deeper underground UGA at Kennedy Airport, but was not found in sounding B. So if anything, one might say, well, yeah, they're very similar, but gee, A is a little bit stronger down here. Well, if we look at shear wave velocities and shear modulus, we see a completely different story. So here we're looking at shear wave velocities, and these are the measured velocities in A and the measured velocities in B. And the calculated, these are the values obtained using the Robinson 2012 empirical correlation that I have always found to be offers the best results. And again, we see for piezocone, seismic piezocone A, we see very good agreement between the measured and the empirical for the entire depth profile. So this would be young, well-behaved, hourglass sands, vanilla soils, whatever you want to call it. Well, if we look at seismic piezocone B, look at the measured data. They diverge significantly from the well-behaved empirical results, and they also diverge significantly from the values measured in A, which only get into not even quite 300. These get beyond 300, 400, 450 meters per second. So these are the same scale, you could see that. Quite a bit difference in the measured values in B as opposed to A. And we see that in the Gmax as well. The small strain shear modulus substantially higher in B as opposed to A. And again, notice the divergence between the measured values and the empirical for B. And this is what I was saying earlier. If you use these empirical relationships that are just based on Q sub C, F sub S, and U2, they will always give you a value. They will always provide you with a number. But they will never tell you, and can never tell you, here's a number, but this number is wrong. All right? They're never going to give you, they're never going to flag a condition where we have structure, where we clearly have here in seismic piezocone B. All right? And the only way to know you have structure or you don't have structure is to take shear wave measurements in the seismic piezocone. And again, this is hopefully really driving home a point that I've made now several times in this presentation. The small strain rigidity index also tells a different story. We see here that in B, we're going beyond the limits of case G, that we don't stray beyond. Here we stay within the well-behaved zone. Again, let's look at our generic chart. Ideal soils, young, uncemented, etc., no structure, are going to fall in this bracket here. Anything that strays to the right is going to soils with microstructure, and we see that in B. All right, notice all these values straying to the right. Well, we can plot up the modulus numbers versus depth, and we can see where this is happening more clearly. Here I'm using the KG3 parameter, and again, we see how within this lower zone here, we are straying beyond the limits of well-behaved soils. Rather interestingly, if we look at age scaling factor, with B, kind of interesting, we're actually trailing towards the tertiary age. All right. So these are suggesting a much older behavioral age compared to what we're seeing in A, what we saw in the seismic piezocone that I used throughout this presentation segment, where we fall between the Holocene, Pleistocene lines. Notice we're straying towards the tertiary line in B. We have structure, right? As I said, this is not just one seismic piezocone. There were a number of seismic piezocones that were more or less identical to this in behavior. Clearly we have structure. Where does it come from? Who knows? My personal guess is that it's somehow related to the complex Pleistocene geology of this area. Again, going back to an earlier slide where we see that Kennedy Airport kind of sits on the rim of this Jamaica Bay salient, where the Hudson Lobe and Connecticut Lobe of the Laurentide ice sheet kind of butted into each other and prevented each other from going farther. Is there some unexplained, unknown glacial behavior occurring here where we have remnants of an older glacial soil? I don't know. This is something that certainly geologists would have to obtain samples of the soils and look at them and see if they can see any difference in the soil particles themselves that could help explain this difference. But we just know that a difference exists. So in summary, this recent terminal project at Kennedy Airport is typified by looking at soundings A and B, is an excellent illustration of the fact that the cone penetrometer tip resistance and shear wave velocity are complementary but not redundant pieces of data. Again, because each addresses a different aspect of soil behavior. Tip resistance measures large strain behavior that is influenced by soil strength and compressibility. So the soils were equally strong. I mean, if anything, down here, A was stronger than B. But when we look at the shear wave velocity, which looks at the linear elastic small strain behavior that's influenced by soil structure due to aging, cementation, etc., we see that B exhibits a much stiffer resistance compared to A. Again, we focus on this lower zone here. This just shows us that the large strain behavior and the small strain behavior are divergent. And this is why it's necessary, in my opinion, on every project, big or small, to run at least one seismic piezocone, measure shear wave velocities, interpret the shear wave velocities, spend that extra few dollars to get this piece of mission critical data. So this just says in words what I've been now saying, that on every project where you're going to use the cone penetrometer, you really need to run seismic piezocones, or don't waste your time and your client's money doing cone penetrometer soundings. On larger projects where we often do site characterization work in phases, it certainly would be desirable to perform at least some of the planned seismic piezocone soundings in the first phase to assess the potential for soil structure. And that's because the presence of soil structure is not even known or suspected beforehand. As I said, I've been working at Kennedy Airport now for over 50 years. There is nothing in the prior knowledge base of Kennedy Airport based on conventional borings and the earlier cone penetrometer soundings that would suggest, hey, you have an area where you have some really interesting different structure. Now, how extensive this area is, I don't know. I don't know of anyone who sat down and looked at all the seismic piezocone soundings ever done at Kennedy Airport and tried to map out where these areas of anomalous structure are. No less try to come up with an explanation as to why this anomaly exists. So certainly this difference in structure was not expected beforehand. And on a site that were, as I said, only a few hundred meters apart from where this difference in behavior was observed. Well, this has been a lengthy presentation, certainly one of my longer ones, and I'd like to wrap it up now with some closing comments. There are three topics I want to touch on, starting off with commoditization of professional services. And this reflects something that I've had some consulting assignments in the last few years involving arbitration in construction that have really given me some insights that bother me, to be honest. I've been in practice over 50 years now, so I've observed a lot of changes in how civil engineering is both taught and practiced. Again, I've spent over 30 years in academia, either full-time or part-time, as a professor, so certainly have experience in that area as well. And one significant area is that a lot of tasks, both in education and practice, have been reduced to a commodity. Management decides, well, anybody could do that. So when you decide something as commodity, then cost becomes the most important consideration for making management decisions. Unfortunately, more times than not, in my experience, this generates a race to the bottom. Who could do it cheaper? I've seen this in academia with the, running out and hiring a lot of adjunct professors instead of full-time faculty. I have nothing against adjunct professors. I was one myself for 6 years. But there's a time and place to use adjunct professors, in my opinion, for their specific knowledge. And unfortunately, there's a time and place where they are used simply because they're cheap labor. Well, enough said on that. The point that I'm getting at, and the reason it troubles me, is that I have personally been involved in many forensic investigations in my over 50 years of practice. In fact, I recently wrote a monograph on geostructural failures that summarizes my more than 50 years of professional experience in this area. And a number of these failures, not all of them of course, but a number of these failures are attributed to the commoditization of which site characterization is one important factor, as it appears in building and design codes. A lot of these codes, especially building codes, they're mired in old technology, such as the standard penetration test that's over a century old at this point in time. So my point is, if a building code says you only have to do standard penetration test and values, well, practicing engineer, if they want to get that job, that's all they're going to do. Because nowadays, more times than not, on small projects, an owner is going to shop for professional services based on cost. So if you come in and say, well, in addition to the standard penetration test that the code says I have to do, I'm going to do some cone penetrometer soundings, well, that's going to push the cost up. And I tell you, you'll lose that job to some other engineer who says, no, I'm just going to do SPT and values, that's it. So all the code says, that's all I'm going to do. So there's no incentive to do something better, such as cone penetrometer soundings. And I think jobs suffer from this eventually. Related to this, I think, in terms of commoditization, is construction project delivery methods. As we all know, there's been a lot of change over the last few decades, especially for large major projects, bridges, highways, things like this. Historically, certainly when I started out in the business, construction projects were delivered on a design, build, bid, build, DBB method, where the design process was contractually segregated and independent of the construction process. So with DBB, an owner, a project owner, would hire a design professional, team of design professionals, architects, engineers. They would be retained by the owner, be paid by the owner, report to the owner. So the project owner controlled all the technical information developed for the project, especially site characterization. Now, in cases where a government or quasi-government agency, such as a state Department of Transportation or Port Authority of New York and New Jersey, which, as I've indicated, has operated Kennedy airports since day one, some role of the engineering was done by design professionals who worked for those organizations. So for the first 27 months of my professional career, I worked for the Port Authority, and we did engineering at Kennedy Airport. So that owner, because it also hired the engineers or employed the engineers, really had total control over the design process. They wanted to spend some extra money to do something like cone penetrometer, well, they would do that. In fact, that's why the cone penetrometer was used in the first place in the late 1980s at Kennedy Airport, because the Port Authority Engineering Department says, you know what, we're going to spend the extra money, we're going to do something that people haven't done historically. We want to use this new tool at the airport. We think it's going to be beneficial. And it turned out to be an understatement. It's been enormously beneficial. So relevant to the present discussion is that under design, bid, build, design professionals retained by the owner, reporting to the owner, exerted a lot of oversight of and input into construction. Contractors really, they functioned as a mechanic executing the work. Now, contractor input was possible. I mean, most projects allowed for a contractor to say, you know what, you specified this material, I'd like to use this material instead. I think there's a time and cost savings. So contractors could still have input, and they might benefit from that input. But it was ultimately the engineer reporting to the owner that had the final say. Well, nowadays the trend in project delivery has been towards design build or design build operate maintain, where the owner contracts with a single business entity at the beginning of a project, and that single business entity is responsible for design, building the project, and sometimes operating and maintaining it for some period of time after completion. So this single business entity is almost always a joint venture of several independent businesses, but in all the cases I've seen, the primary member is a large construction firm, very often internationally owned, not owned here in the United States. So it has the international ownership and presence. I mentioned that not in a negative, but it does make one think, you know, if the primary organization doing the work is based outside the U.S., are they still going to be around years from now to answer for their work? I think that's a reasonable question to ask. Well, of course, everybody has locked on to this design build or design build operate maintain. It's always presented as a win-win situation for all concerned. It's better for everybody. It certainly simplifies the life of a project owner, as they only have to hire one business entity, and that's all they have to monitor. Furthermore, it pushes the risk of delivering and possibly operating and maintaining a project onto that business entity. So, you know, from an owner's perspective, there appears to be a lot to like. I've often seen it said, well, you know, it's going to give you a better product, right? You're going to have a seamless process. You have a single organization. It could be innovative. It's going to give you the best product at the lowest cost and the least amount of time. You're not going to have any of these RFIs, requests for information, where a contractor has to ask an owner and the owner's engineer, gee, I want to do this. Can I do it? There's not going to be change orders for unanticipated conditions. There's not going to be claims for extras for unanticipated conditions. So all of the construction-related contract issues that almost always come up in conventional design, bid, build, theoretically at least, don't exist in design, build, right? What's not to like, right? You're going to get the best thing at the lowest cost and the least amount of time, or so they say. And I like to refer to this as the one big happy family syndrome. All right, these joint ventures that I've seen are presented to an owner as, this here we do everything. We'll design it for you, we'll build it for you, we'll operate it for you. The one big happy family. My personal experience, my professional experience, these are not one big happy family. As I said, in recent years, I've had the opportunity as an expert witness to be involved in litigation, arbitration that have involved these design, build, operate, maintain contracts. And I will tell you from firsthand experience, there are a lot of problems that come up. They are not the traditional problems, they're different problems, but they're problems nonetheless. And I think there are certainly possibilities for a lot more losses than wins with this modern way of doing things. There's a lot of reasons. I could go on talking for some period of time about this. I think relevant to the present discussion is that whether you like it or not, on these design, build, and operate, maintain projects, the joint venture tends to be dominated, and I mean dominated, by the contractor, simply because the dollar value of actually building things is a lot more than designing it and operating it and maintaining it. So the contractor, which I said is nowadays often an international, multinational corporation, very often based outside the United States, they are going to come in and rule things with an iron fist because they have the biggest dollar exposure for the actual construction. This puts a lot of pressure on the design engineer because now the design engineer is working for the contractor. They're beholden to the contractor. If they want to get paid on that project, if they want to be involved in future projects. And this is a big issue a lot of people don't like to talk about. It used to be, when I worked in consulting, you would always want to design a good product because you could go to other owners and say, look what I have done for other owners. I have designed this really nice product for them. Well, now with DB or DBOM, the design professionals have to go to contractors and they have to say, look what I've done for this other contractor. Look how much money I saved them. Look how fast I did the work. Look how many corners I cut to get there. So the design professionals, both in the present as well as for their future existence, they have to keep contractors happy, not owners happy. They have to keep contractors happy. Well, how does a design engineer keep a contractor happy? They have to deliver a design concept for as little money as possible in the fastest time possible. And they have to come up with something that can be built fast and built cheap and only does what it has to check all the boxes to comply with some codes and design manuals that are specified in the contract. I've seen firsthand what a lot of these design, build, operate, maintain contracts look like. And typically they say, you joint venture design build team, you have to follow this code and this code and that code and this manual on how to design deep foundations or whatever. So there are any number of legal boxes that have to be checked in the design. So what I've seen happen is that the minimum is done to meet the letter of the law and not the spirit of the law. There are cases where, and this was what happens when all of a sudden now you want to build a bridge that's a little bit longer that's been built before. Or you want to put in a drilled shaft that's a little bit larger diameter than has been drilled in this area before. So when you're looking to push the envelope of design, you want to build something longer, you want to build something heavier, you want to build something deeper, a bigger diameter than been done before. These are cases, in my professional opinion, where you perhaps need to do a little bit more than what the code specifies. When you're venturing off into the unknown, I think it is prudent, good engineering to go above and beyond the letter of the law. And that's the spirit, that's what I mean by spirit of the law. You have to look at, say, well, we're trying to do something in this area that's never been done before. Maybe we need to do a little bit something extra. I use in a case in point that I'm aware of. When the original World Trade Center towers were constructed, designed and construction in the late 1960s, these were basically supported on spread footing sitting on bedrock. Now, high-rise buildings sitting on bedrock is something that had been done in Manhattan Island in New York City for a very, very long time. This was not something new. All of the tallest buildings in Manhattan Island, on Manhattan Island in New York City up to that point in time, were supported on spread footings to bedrock. Bedrock that was exposed in an open cut excavation. However, obviously at that time, the original World Trade Center towers were going to be the tallest buildings in the world. So, although high-rise buildings have been built on bedrock in Manhattan Island on footings for a long time, when you're designing and going to build the tallest buildings in the world, you're going to be pushing the envelope. So what they did is they actually built full-scale mock-ups of the proposed spread footings, and they jacked them into the ground to measure a load settlement curve. They did not rely on allowable bearing values in the City of New York Building Code for footings on bedrock. They could have done that, but they didn't. Why? Because they were pushing the envelope. They were building something that was taller and heavier than had ever been supported on footings on bedrock before. So the prudent decision was, let's go beyond what the building code requires. We're going to build a full-size mock-up and we're going to jack it into the ground. We're going to see how the rock behaves. So that's what I'm getting at here. In my personal experience, the current methods of project delivery, I don't see this happening to the extent that it should. Again, that's a professional opinion. Why am I bringing this up here? Well, I've seen with these projects, these joint ventures tend to hoard the technical knowledge they produce during the project. And they hoard this for their perceived future business advantage and gain. Their thinking is, well, I've done this, so I'm gonna hold this close to the vest. I'm not going to share this knowledge. I'm not going to write papers about it because I might be able to use it to my advantage to get a project in the future. And I have seen cases where even the project owner was denied access to technical knowledge. There's one specific case. I'm not going to get very specific about it because I don't want specific organizations and names to come up. But it was a case in the New York City metropolitan area where the owner of a project, who I knew people who worked for the owner, and I was doing some research on taper-driven piles. So I went to the owner and say, hey, I know you've got this project going on. You're using tapered piles. Could I have copies of the subsurface information and the pile driving logs? Because I want to use this for my tapered pile research. And the owner says, sure, I'll talk to the contractor I've hired to do this. Well, they come back to me later and say, the contractor says they don't want to give us that information. And I was astounded. Here you have an owner of this facility, and the contractor hired says, no, we're not going to tell you what the subsurface conditions are, and we're not going to tell you how deep the piles drove, because we're going to hold on to this. We paid for this, so we're going to keep this knowledge ourselves. I was absolutely astounded. And that's the context I'm bringing it up here, in the context of site characterization. Oh, the final thing I want to talk about is additional uses of the cone penetrometer. This presentation has intentionally been limited to using the piezocone, the seismic piezocone, for site characterization, and making the point that these devices are mission critical on both large and small projects. The follow-on that I did not address in this presentation is that the data you obtain from cone seismic piezocone and piezocone soundings and the soil properties and parameters that you post-process and obtain can be used for a wide variety of design applications. We can use them in what we call the indirect method or rational method, where we take the raw data, the QC, FS, U2, and V sub S, translate this into material properties as I've shown you in this presentation, plug those numbers into some analytical method that is usually theoretical and generic, and you get a calculated outcome. You get a pile capacity, you get a footing settlement, whatever. Alternatively, we could use these data from a cone penetrometer sounding in what is called the direct method, where we go right from the raw data into some analytical method that is usually application specific and empirical, and you get a calculated outcome. So, for example, there's no shortage of analytical methods for using cone penetrometer data for, say, the axial compressive geotechnical resistance of a deep foundation, a driven pile, drilled shaft, board pile, whatever you want to call it. So you skip the intermediate process of coming up with the material properties. But the point is that the fact that the cone penetrometer offers a wide variety of possibilities beyond site characterization really increases the cost effectiveness of using this tool in both practice and research. And I'll just point out, for the sake of completeness, that two of the publications I've mentioned in this presentation illustrate this last point. Both are in the public domain, and you can find them online. One is the Minnesota DOT document that was prepared with the assistance of Dr. Main, and this contains quite a bit of methods for and worked examples for using the direct method application of cone penetrometer data for both shallow and deep foundations, for both footings and piles, drilled shafts, etc. The drilling guide that was prepared by Dr. Robertson, this guide also contains some guidance on the use of cone penetrometer data in geotechnical and foundation analysis. So these two documents are both useful for the design-related applications using cone penetrometer data. And with that, I would like to bring this lengthy presentation to a close and say thank you very, very much for your interest and attention. And I hope you found the information I presented useful in your current and future work using the cone penetrometer.